Wave-particle duality. Wave-particle duality is one of the most fascinating and perplexing principles of quantum mechanics. At its core, it suggests that all matter and energy possess both particle-like and wave-like properties. This paradoxical concept arises from the observation that elementary particles, like electrons or photons, can sometimes behave as particles and at other times as waves, depending on the conditions under which they are observed. The implication of this discovery challenges our conventional understanding of the universe, where objects are clearly divided into categories, either waves or particles. Instead, quantum mechanics proposes a more complex and fluid reality, where the behavior of matter and energy is not fixed, but context-dependent. The essence of wave-particle duality becomes clearer when we consider light. Traditionally, light was thought to behave purely as a wave, as evidenced by phenomena such as interference and diffraction. However, the situation evolved with the work of Albert Einstein, who explained the photoelectric effect in 1905. Einstein demonstrated that light could also behave as discrete packets of energy, or quanta, later named photons. This discovery suggested that light, once considered purely a wave, also had particle-like characteristics. This led to the development of quantum theory, which asserts that all fundamental particles can exhibit both wave-like and particle-like properties, depending on the experimental setup. For example, the famous double-slit experiment, first conducted by Thomas Young in 1801, vividly illustrates the dual nature of light. In this experiment, light is shown through two closely spaced slits onto a screen. If light behaves as a wave, it will produce an interference pattern, where the waves overlap and amplify or cancel each other. This pattern is characteristic of waves, and was observed when light was passed through the slits. However, when the experiment was repeated, with light being emitted one photon at a time, the interference pattern still appeared, suggesting that each photon interfered with itself as if it were a wave. But when detectors were placed at the slits to observe which slit the photon passed through, the interference pattern disappeared, and light behaved purely as particles. This paradox shows how observation itself influences the behavior of light, reflecting the fundamental mystery of quantum mechanics. This concept was later expanded to include not only light, but also matter, especially electrons. Louis de Broglie proposed in 1924 that all matter, not just light, exhibits both particle and wave properties. His hypothesis was confirmed by experiments involving the diffraction of electrons, suggesting that even objects like electrons, which are classically thought of as particles, can behave as waves under the right conditions. This discovery shook the foundations of classical physics, as it presented a world where the boundaries between waves and particles were no longer clear. Wave-particle duality forces us to rethink the very nature of reality. It suggests that the properties we observe in the world are not inherent in objects, but are influenced by how and what we choose to measure. The duality highlights a fundamental tension in our understanding of the universe. Do particles have a definite position, or do they exist in a range of possibilities until observed? This paradox is part of the ongoing debate about the nature of quantum mechanics, and it challenges our ability to reconcile the rules of the quantum world with the physical reality we experience. Wave-particle duality also has profound implications for how we understand the universe. It suggests that at the quantum level, the distinction between particles and waves is not absolute, and the nature of reality is far more fluid and complex than classical physics would have us believe. It brings into question the nature of observation and measurement, implying that reality is not fixed but exists in a superposition of possibilities until observed. This shift in perspective compels us to reconsider our deepest philosophical questions about existence, causality, and the role of the observer. Despite its somewhat abstract nature, wave-particle duality has numerous practical applications. In the field of technology, it is foundational to the development of quantum computers, which leveraged the wave-like behavior of particles to perform calculations that would be impossible using classical methods. Additionally, the principles of wave-particle duality underpin technologies such as electron microscopy, where the wave nature of electrons allows for imaging at atomic scales, far beyond the reach of traditional light microscopes. The phenomenon is also crucial to understanding the behavior of semiconductors and the functioning of devices like transistors and lasers, which have become ubiquitous in modern electronics. There are several common misconceptions about wave-particle duality. One of the most prevalent is that particles and waves are two separate, distinct categories. In reality, the behavior of particles and waves is not mutually exclusive. Particles can exhibit wave-like properties and vice versa, depending on how they are observed. Another misconception is that wave-particle duality implies that all particles are somehow both at the same time. While particles do exhibit both wave-like and particle-like behaviors, this does not mean they are simultaneously both. Instead, it depends on the experimental conditions and the type of measurement being made. The role of the observer is also often misunderstood. The act of measurement does not force a particle into one state or the other, but reveals which aspect of its nature is more relevant in that context. In closing, wave-particle duality remains one of the most profound and/or inspiring revelations of modern physics. It compels us to acknowledge that the universe, at its deepest level, is more mysterious and enigmatic than we could have ever imagined. The interplay of waves and particles challenges the very way we think about matter and energy, offering a glimpse into a world that operates on principles far beyond the grasp of our everyday experiences. It is a reminder that the pursuit of knowledge is not merely about finding answers, but about embracing the mysteries that drive us to question everything we thought we knew. Superposition. Superposition is a concept that challenges our deepest intuitions about reality. At its heart, it suggests that a quantum system can exist in multiple states simultaneously, a notion that feels almost impossible when contrasted with our everyday experiences. Unlike classical objects that occupy a single place at a single time, particles at the quantum level defy this certainty, existing in a spectrum of possibilities until measured. This defiance of singularity invites reflection on the nature of existence itself, hinting at a reality that is far more fluid and intertwined than the linear world we perceive. The mechanics of superposition are embedded within the mathematical framework of quantum theory. A particle is described by a wave function, an abstract entity that encodes all the potential states the system can occupy. These states are not mere hypothetical alternatives. They coexist, each contributing to the overall behavior of the system in a measurable way. Only when an observation is made does the system appear to collapse into one definitive state, as if reality had been waiting for our attention to solidify its form. This interplay between potentiality and observation reveals a subtle tension between what is possible and what is actual, a tension that has profound implications for our understanding of causality and determinism. Evidence for superposition is compelling and elegant. The double-slit experiment offers a striking visualization, where electrons passing through two slits create an interference pattern that could only arise if each electron traversed both paths simultaneously. Even when electrons are sent one at a time, the pattern gradually emerges, suggesting that each particle exists in a superposed state until measured. Similarly, experiments involving entangled particles demonstrate that superposition is not confined to isolated systems. Measurement of one particle instantaneously influences the state of its partner, revealing a universe that is deeply connected and non-local. These experimental results are not merely technical curiosities. They are windows into a reality that operates on principles that defy conventional logic. The implications of superposition are as unsettling as they are profound. It challenges the classical notion of an objective reality independent of observation, suggesting that the act of measuring is inseparable from the nature of what is measured. The idea that particles can occupy multiple states simultaneously forces us to reconsider the linearity of time, the definiteness of objects, and even the concept of identity itself. Superposition invites a philosophical reflection on uncertainty and possibility, prompting questions about whether reality is fixed or fluid, whether the universe is deterministic or probabilistic at its core. It is a reminder that the world may be far stranger and more wondrous than our senses allow us to perceive. Despite its abstract nature, superposition has tangible applications that are reshaping technology. Quantum computing exploits superposition to perform calculations that would be impossible for classical computers, leveraging the ability of qubits to exist in multiple states simultaneously. Quantum sensors and imaging techniques take advantage of these principles to achieve unprecedented sensitivity and precision. Even in cryptography, superposition underpins protocols that ensure secure communication by exploiting the delicate balance between potential states and measurement. These applications demonstrate that the strangeness of superposition is not merely theoretical, but a tool that can be harnessed to expand human capability and understanding. Common misconceptions about superposition abound. It is often imagined as a particle physically being into places at once in the ordinary sense, rather than as a mathematical description of probabilities. Another misunderstanding is the belief that observation creates reality in a mystical sense. In truth, it is the interaction with a system that resolves potential outcomes into observable phenomena. Clarifying these subtleties is essential to appreciate both the conceptual elegance and the practical relevance of superposition, separating poetic exaggeration from the precise and testable framework that science provides. In closing, superposition is a doorway into the quantum landscape, a realm where certainty is provisional and possibilities coexist. It evokes awe because it defies instincts and invites a deeper contemplation of what it means to exist. By probing the boundaries between potential and actuality, superposition illuminates a universe that is simultaneously precise and mysterious, deterministic and probabilistic. It reminds us that the fabric of reality may be far more intricate than we can intuitively grasp, offering both scientific insight and philosophical reflection. In the quiet presence of this paradox, one is left with a profound sense of wonder at the subtle, intricate, and deeply beautiful structure of the world. Measurement affects reality. Measurement is a cornerstone of human understanding. It is through measurement that we are able to quantify the world around us and make sense of our surroundings. Whether it is the length of a table, the time it takes to run a mile, or the temperature of a cup of coffee, measurement provides the language we use to describe and navigate the physical universe. But what if measurement itself is not simply a passive tool we use to understand reality, but an active participant in shaping it? In classical science, the world was seen as an objective entity, independent of the observer. The universe was thought to function according to fixed laws that existed whether or not humans were around to measure them. However, as science progressed, particularly in the realms of quantum mechanics and the philosophy of science, this view began to be questioned. The very act of measuring something in the quantum world, like the position or momentum of a particle, seems to change the state of that thing. The more precisely we measure one property, the less we can know about another. This principle is known as the Heisenberg uncertainty principle. What we measure, in some deep sense, shapes the very nature of what we measure. At the heart of this idea is the realization that measurement is not a neutral process. When we measure something, we interact with it, and in doing so, we influence its properties. In quantum mechanics, particles like electrons can exist in multiple states at once, known as superposition. But once we measure them, they collapse into a single state. This behavior has led some scientists to speculate that the very act of observing or measuring a system forces it to choose a specific outcome. This suggests that our measurement itself could be altering the reality we are attempting to understand. There are various experiments that highlight this strange relationship between measurement and reality. One of the most famous is the double-slit experiment. In this experiment, particles like electrons are fired at a barrier with two slits, and the resulting pattern of particles hitting a detector screen is observed. When the particles are not being measured, they behave like waves, creating an interference pattern. But when a measurement is made to determine through which slit the particles pass, the interference pattern disappears, and the particles behave as though they have passed through one slit or the other. This shift in behavior upon measurement demonstrates the profound effect that observation has on the system being observed. This phenomenon is not limited to subatomic particles. It extends to the macro world in more subtle ways. One example is the observer effect in social sciences. In psychology, the Hawthorne effect describes how people alter their behavior when they know they are being observed. Even something as abstract as the act of counting can influence the reality being measured. For instance, a community might start to engage in healthier behaviors simply because a public health study begins to track their eating habits. The mere awareness of measurement changes how they behave, and thus changes the outcome. The most puzzling aspect of this concept is the deep philosophical question it raises. Is reality truly independent of us, or are we co-creators of the universe we observe? If the act of measurement influences reality, then how much of what we perceive as objective truth is merely the result of our own interactions with the world? This idea challenges the very foundation of scientific inquiry, which assumes that reality exists regardless of whether we are there to observe it. If our measurements can change the world, how can we ever know what is real? This paradox has profound implications for how we approach knowledge and science. It suggests that reality is not something that can be fully separated from the observer. Our understanding of the world is inextricably linked to the tools and methods we use to measure it. This interconnection calls into question the idea of objective reality. Perhaps what we think of as objective is simply a collective agreement on how we measure and observe the world. In the real world, these ideas are not just philosophical musings. They have practical implications for fields ranging from quantum computing to medical imaging. Quantum computing, for example, relies on the principles of superposition and entanglement, where particles exist in multiple states until they are measured, allowing them to perform computations far beyond the capability of classical computers. Similarly, medical imaging techniques like MRI scans depend on the measurement of magnetic fields within the body to generate images of internal organs. But in both cases, the act of measurement is not without consequence. It alters the very systems we are attempting to understand. Despite these advancements, there are still many misconceptions about the relationship between measurement and reality. One common misconception is that measurement simply reveals an objective truth that exists independently of the observer. In fact, as we have seen, measurement plays an active role in shaping the observed reality. Another misconception is that the effects of measurement are limited to quantum mechanics. While it is most obvious in the subatomic world, the observer effect can be found in many other domains, from psychology to sociology. In conclusion, the idea that measurement affects reality forces us to reconsider what we know about the world. It suggests that reality is not a fixed, unchanging thing, but rather something that is shaped by our interactions with it. The more we probe the universe with our tools of measurement, the more we come to understand that the line between the observer and the observed may be blurrier than we ever imagined. This realization opens up new possibilities for how we think about science, knowledge, and the very nature of existence itself. Quantum entanglement. Quantum entanglement is a phenomenon in quantum physics where two or more particles become linked in such a way that their states are interdependent, even when separated by vast distances. This strange and puzzling phenomenon challenges our classical understanding of reality and has left scientists and philosophers alike in deep contemplation. At its core, quantum entanglement reveals that the nature of particles is not as isolated or independent as once thought. The behavior of one particle or an entangled pair influences the other instantaneously, regardless of the space between them. This connection transcends space and time, offering a glimpse into the deeply interconnected fabric of the universe. The workings of quantum entanglement are rooted in the principles of quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales. When two particles become entangled, their properties, such as spin, charge, or polarization, are no longer independent. Instead, their individual states are intertwined in such a way that altering one particle's state will immediately influence the other, even if they are light years apart. This instantaneous influence, often referred to as spooky action at a distance, challenges the very notion of locality, that objects can only affect one another through direct interaction within their immediate surroundings. According to quantum mechanics, however, entangled particles can influence one another instantaneously, making it as though they share a common existence, no matter the distance. One of the most celebrated experiments providing evidence for quantum entanglement is the Bell's theorem experiment, first proposed by physicist John Bell in the 1960s. Bell theorized that if quantum mechanics were true, then entangled particles would violate certain inequalities that were assumed to hold in classical physics. In the decades that followed, experiments designed to test Bell's inequalities were conducted, with the most famous being those by physicist Elaine Aspect in the 1980s. These experiments demonstrated that entangled particles indeed violated Bell's inequalities, providing strong evidence that quantum entanglement is a real and fundamental aspect of nature. The results of these experiments not only validated quantum theory, but also marked a pivotal moment in our understanding of reality, suggesting that the universe operates in ways that defy our everyday experience. Quantum entanglement is unsettling because it seems to defy logic and common sense. It raises profound philosophical questions about the nature of reality, causality, and the limits of human perception. If particles can influence one another across vast distances without any physical connection, what does this imply about the fundamental structure of the universe? Are we witnessing a kind of cosmic interconnectedness that transcends time and space, a network of relationships that binds everything together? The very idea that information can travel faster than the speed of light challenges the foundations of relativity, one of the pillars of modern physics. While no information can actually be transmitted faster than light due to the no-signaling theorem, the fact that entangled particles are so deeply connected still leaves us wondering about the nature of reality itself. The implications of quantum entanglement extend far beyond philosophical musings. This phenomenon has practical applications that are beginning to reshape the future of technology. One of the most promising uses of quantum entanglement is in the field of quantum computing. In a quantum computer, qubits, the quantum counterpart of classical bits, can exist in multiple states simultaneously, thanks to superposition and entanglement. This allows quantum computers to perform complex calculations much faster than classical computers, solving problems that would take classical computers millennia to process. Entanglement is also crucial for quantum cryptography, which promises to create ultra-secure communication systems. In this context, entanglement is used to ensure that any attempt to eavesdrop on a communication would immediately alter the entangled state, revealing the intrusion. Despite its groundbreaking potential, quantum entanglement is often misunderstood. One common misconception is that entangled particles communicate instantaneously, as if they send messages to each other across space. However, this interpretation is incorrect. Entanglement does not involve any direct signal or information transfer between the particles. Instead, it is a correlation between their states, with the measurement of one particle's state instantly determining the state of the other, even though no information is actually transmitted. Another misconception is that entanglement violates the speed of light limit set by relativity. While entanglement does involve an instantaneous connection between particles, it does not violate relativity because no usable information is transmitted faster than light. In conclusion, quantum entanglement offers us a profound glimpse into the nature of reality. It shows us that the universe is far more interconnected than we ever imagined, and that the laws of physics, especially at the quantum level, defy the intuitive concepts that govern our everyday world. It challenges our understanding of space, time, and causality, prompting us to rethink our assumptions about how the world works. And as science continues to unravel the mysteries of quantum entanglement, we may find that this strange phenomenon holds the key to a new era of technological innovation and a deeper understanding of the cosmos. Perhaps, in time, it will also reveal a truth about the universe, that everything is connected in ways we are only beginning to comprehend. Instant correlations, entanglement. Entanglement is one of the most profound phenomena of quantum mechanics, a feature so perplexing that even the most seasoned physicists have struggled to fully comprehend its implications. At its core, entanglement describes a state where two or more particles become connected in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. These particles, once entangled, exhibit a behavior that transcends conventional notions of space and time. What makes this concept so baffling is that these correlations appear to occur instantaneously, defying our classical understanding of causality and the speed of information transfer. Entanglement works by linking particles in a quantum state such that the properties of one particle, such as its spin, momentum, or polarization, are directly tied to those of another. When a measurement is made on one of the entangled particles, the other particle's state is immediately determined, no matter how far apart the two are. This is not merely a correlation of probabilities, but a definitive connection that defies any classical explanation. It is as if the particles are aware of each other's states, even as they are light years apart, a concept that seems to challenge the very nature of reality itself. The most significant experimental evidence for quantum entanglement emerged from the work of physicist Albert Einstein, whose skepticism led him to famously call entanglement spooky action at a distance. Yet, it was physicist John Bell and his collaborators who, in the 1960s, formulated Bell's theorem, which provided a framework for testing entanglement. Bell's inequalities, as they came to be known, set the stage for experimental tests of quantum mechanics versus classical physics. Numerous experiments have since confirmed the predictions of quantum mechanics, demonstrating that particles do indeed exhibit instantaneous correlations, even when separated by vast distances. Perhaps the most famous of these experiments came from Elaine Aspect in the 1980s, who demonstrated that the entangled particle's behavior could not be explained by any local hidden variable theory, further solidifying the reality of quantum entanglement. The implications of entanglement are nothing short of revolutionary. If particles can be instantaneously linked in this manner, it suggests a deeper, underlying connectivity between the fabric of reality itself, one that may not be constrained by the limits of space and time. This challenges the classical concept of locality, the idea that objects are only influenced by their immediate surroundings. It also pushes the boundaries of causality, which has been one of the cornerstones of both physics and philosophy for centuries. The very idea that information could travel faster than light, or that particles could instantaneously communicate across vast distances seems to defy the conventional wisdom established by relativity and everyday experience. Entanglement forces us to question our understanding of the universe at the deepest level. However, the weirdness of quantum entanglement does not stop at the conceptual. In fact, it seems to have birthed an array of philosophical quandaries. One of the central questions is whether entanglement implies a form of non-locality, where the universe is connected in ways that cannot be explained by the standard rules of space and time. This would suggest that reality itself is far more interconnected and interdependent than we can currently imagine. Such ideas open up debates about determinism and free will, about the nature of the observer in quantum mechanics, and about the very concept of reality itself. The more we delve into the realm of quantum physics, the more our intuitive understanding of the world becomes challenged, leaving us with a sense of awe and wonder. In the real world, quantum entanglement is not just a theoretical curiosity. It has practical applications. One of the most promising fields of application is quantum computing, where entangled particles, or qubits, are used to perform calculations that would be impossible for classical computers. In a quantum computer, the entangled state of qubits allows for the simultaneous processing of multiple computations, exponentially increasing processing power. Another application is quantum cryptography, which uses the principles of entanglement to create virtually unbreakable encryption systems. The inherent security of quantum communication systems ensures that any attempt to intercept or measure the entangled particles would disrupt their state, rendering any potential eavesdropper's efforts detectable. Despite its revolutionary potential, there are many misconceptions surrounding quantum entanglement. One common myth is that entanglement allows for faster-than-light communication. While it is true that entangled particles influence one another instantaneously, this does not mean that information can be transmitted faster than light. The process of measuring an entangled particle does not allow for controlled communication, as the outcome of the measurement is fundamentally random. Another misconception is that entanglement somehow involves particles talking to each other across space. In reality, entanglement does not imply any form of classical communication or signal transmission, but rather a shared quantum state that is revealed only when a measurement is made. In closing, quantum entanglement stands as one of the most intriguing and mysterious phenomena of modern physics. It compels us to rethink our deepest assumptions about the nature of reality, locality, and time. While its practical applications hold great promise, the true philosophical and scientific significance of entanglement is still unfolding. As we continue to explore this strange and awe-inspiring aspect of the quantum world, we are reminded of how little we truly know about the fabric of the universe, and how much there still is to learn. In the end, the study of entanglement may well lead us to a more profound understanding of the interconnectedness of all things. Quantum tunneling. At the core of quantum mechanics lies a paradox so strange that it challenges our deepest intuitions about the fabric of reality itself: quantum tunneling. It defies the conventional understanding of physics, a reality where particles defy the very laws of classical mechanics to pass through barriers that, according to Newtonian laws, should be insurmountable. It is as though the rules that govern the large-scale universe simply do not apply at the minute quantum scale. The essence of quantum tunneling is rooted in the concept of probability. In the quantum world, particles do not exist in a single defined state as they do in the classical world. Instead, they exist in a blur of probabilities. These particles, such as electrons, do not have specific locations or speeds until they are measured. Their position is described by a probability wave that spreads across space. The act of measurement causes this wave to collapse, pinpointing the particle in a specific location. However, before this collapse, the particle's wave function can extend beyond barriers that would be considered impenetrable by classical standards. In essence, quantum tunneling allows particles to tunnel through barriers, even though they do not have enough energy to surmount them in the traditional sense. This phenomenon is not a metaphor. It is an intrinsic feature of how particles behave on the smallest scales. The experimental verification of quantum tunneling emerged in the early 20th century and was soon solidified through direct observation. One of the most striking pieces of evidence came from the study of radioactive decay. Certain isotopes of elements, like uranium, would undergo alpha decay, where an alpha particle, a helium nucleus, would escape from the nucleus. Classical physics suggested that the alpha particle did not have enough energy to overcome the strong nuclear force binding it inside the nucleus. Yet, experiments confirmed that these particles did indeed escape. The explanation, rooted in quantum mechanics, was tunneling. The particle, despite lacking the classical energy to escape, would quantum mechanically tunnel through the potential barrier that surrounded the nucleus. Another pivotal experiment involved the scanning tunneling microscope, which operates on the principle of quantum tunneling. This device allows scientists to manipulate and visualize individual atoms by using a sharp tip that scans a surface. The tip does not physically touch the atoms. Rather, it tunnels across the surface, an effect that was first theorized in 1928 by physicist George Paget Thomson. The fact that we can observe and manipulate individual atoms is a direct testament to the weirdness of quantum tunneling, offering a concrete, accessible manifestation of an otherwise elusive phenomenon. To fully grasp the strangeness of tunneling, one must appreciate the fundamental difference between classical and quantum worlds. In classical mechanics, particles are subject to definite positions and velocities. They obey deterministic laws. In the quantum realm, uncertainty reigns. A particle's location is not fixed, but probabilistic. This uncertainty leads to behaviors like tunneling, where the conventional wisdom breaks down, and particles are free to defy barriers that we might consider insurmountable. This challenges not only our physical understanding, but our very conceptions of time and space, for the particle seemingly acts as though it knows the barrier is permeable. A concept that resonates deeply with both the unpredictability of nature and our own philosophical reflections on determinism and free will. Quantum tunneling has profound implications across multiple fields. In particle physics, it is central to the functioning of stars, where nuclear fusion occurs because particles can tunnel through energy barriers that would otherwise prevent such reactions. In electronics, quantum tunneling enables the operation of modern devices, such as tunnel diodes and flash memory, where the controlled flow of electrons across barriers leads to faster and smaller components. The implications of tunneling reach far beyond the laboratory, influencing the most fundamental processes that sustain life on Earth, and powering the devices that drive the modern world. Despite the power of quantum mechanics, there are still many misconceptions surrounding tunneling. One common misunderstanding is that particles move through barriers in the way that we would understand motion in the classical sense. In reality, tunneling is not the particle traveling through the barrier in a straightforward manner. Rather, it is a consequence of the wave function's probability amplitude, which is spread across space. The particle does not traverse the barrier. It simply has a probability of being found on the other side. It is not an action that can be directly observed, and this abstract quality often leads to confusion. Another misconception is the notion that quantum tunneling occurs only at the subatomic scale. While it is most commonly observed in particles like electrons, tunneling has been proposed as a mechanism that could potentially play a role in the behavior of larger systems, though this remains a topic of debate and investigation. On the other hand, tunneling does not mean that anything can pass through barriers. The probability decreases exponentially as the barrier becomes larger or the energy required for tunneling becomes greater, which is why we don't see everyday objects tunneling through walls. In conclusion, quantum tunneling challenges not only our physical understanding, but also our philosophical view of the universe. It is a phenomenon that stretches our imagination, forcing us to confront the limitations of our own reasoning and question the very nature of reality. What tunneling reveals, more than anything, is the vast gulf between our macroscopic experiences and the microscopic world that underpins them. It serves as a reminder that the universe, in all its complexity, is still full of mysteries waiting to be unraveled, inviting us to delve deeper into its hidden dimensions. As we continue to explore the quantum realm, tunneling will undoubtedly remain a source of wonder and inquiry, forcing us to rethink the boundaries of what is possible. Electron probability clouds. The concept of electron probability clouds lies at the heart of quantum mechanics, a field that delves into the fundamental nature of reality. These clouds represent the regions around an atom's nucleus where an electron is most likely to be found. The term probability is essential here, for it underscores the inherent uncertainty of the quantum world. Rather than being a simple path or orbit, the electron exists in a wave-like state, with a range of probabilities dictating where it may appear at any given time. This reality stands in stark contrast to classical physics, where objects are thought to have precise locations and predictable behaviors. Electron probability clouds emerge from the solution to Schrödinger's equation, a mathematical framework that describes how quantum systems evolve over time. When applied to atoms, the solutions show that electrons do not have definite orbits like planets around the Sun. Instead, their locations are represented as a distribution of probabilities. This distribution forms a cloud in three-dimensional space, with varying density. The denser the cloud, the greater the probability of finding an electron in that region. In this way, the electron's position is not fixed, but is spread across a range of possibilities. The principles behind electron probability clouds have their origins in the work of early quantum theorists, most notably Niels Bohr and Werner Heisenberg. Bohr's model of the atom, which introduced quantized energy levels, was revolutionary for its time. However, it failed to fully account for the observed behavior of electrons. This limitation led to the development of the more advanced quantum mechanical model, where Heisenberg's uncertainty principle played a crucial role. The uncertainty principle asserts that one cannot precisely measure both the position and momentum of an electron simultaneously. This idea is not merely a limitation of our measuring tools, but a fundamental characteristic of nature itself. The electron, therefore, cannot be pinned down to a specific location in the way classical particles can. Key experiments have further substantiated the existence of electron probability clouds. The famous double-slit experiment is perhaps the most illustrative. When particles, such as electrons, ascend through two slits, they create an interference pattern typical of waves. This result challenges the classical understanding of particles, which would have been expected to pass through one slit or the other. Instead, the electron behaves as a wave, with its probability of being detected in different locations spread out. This phenomenon, often described as wave-particle duality, confirms that the electron exists in a cloud of probabilities until it is measured. Only at the moment of observation does it collapse into a definite position. Why, then, do these clouds appear so strange? It is not just the fact that electrons behave unlike anything we encounter in daily life, but the very nature of their probability clouds challenges our intuition. The electron does not have a clear, distinct place. It is not something that can be pinned down in a specific way. This uncertainty and the idea that an object's position is not determined until it is measured shake the foundations of classical determinism. It forces us to reconsider the deterministic universe that Newton described, a universe where the position and movement of every object can be known and predicted. In quantum mechanics, the universe is probabilistic, not deterministic, suggesting that there is an intrinsic randomness to nature. In real-world applications, electron probability clouds are more than a theoretical curiosity. They form the basis of modern technologies that we rely on every day. The design of semiconductors, for example, depends on understanding the behavior of electrons within atoms. The principles of quantum mechanics, which describe the probability clouds of electrons, underpin the workings of transistors, lasers, and various other devices critical to electronics and computing. Even the field of quantum computing, which holds the potential to revolutionize how we process information, relies on the principles of superposition and entanglement phenomena that emerge directly from the probabilistic nature of electrons. Despite the importance of electron probability clouds, there remain numerous misconceptions. One common misunderstanding is the notion that the electron is physically spread out across a cloud. This is not quite accurate. The cloud is not a physical object but a statistical description. It tells us where an electron is likely to be found if we look, not where it is at any given moment. Another misconception is that the electron, when unmeasured, is everywhere at once. In truth, the electron exists in a range of probabilities, and when it is measured, its position becomes definite. The wave-like nature of the electron does not mean that it spreads out in the way a liquid or gas would. It simply means that its potential locations are diffused across space in a way that defies classical intuition. As we peer deeper into the quantum realm, we confront the idea that reality at its most fundamental level is not what we imagine it to be. The electron probability cloud forces us to abandon the comforting notion of a deterministic, mechanical universe. Instead, it presents a world of possibility, of uncertainty, and of probabilities that only resolve into certainty once we observe them. And yet, this strange, intangible world is not merely theoretical, it is the very fabric of the universe, shaping the material world we experience daily. The more we learn about the electron's behavior, the more we realize that reality itself may be far more complex and mysterious than we ever imagined. It is a humbling reminder that what we know is only the surface of a much deeper, far more intricate story waiting to be uncovered. Heisenberg uncertainty principle. The Heisenberg uncertainty principle is the cornerstone of quantum mechanics that challenges the classical intuition of the world. It articulates a fundamental limitation on the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. Unlike measurement errors in everyday experience, this limitation is intrinsic to the nature of reality. It is not a matter of flawed instruments or experimental design, but a reflection of the very structure of the quantum universe. In the world of atoms and subatomic particles, certainty is replaced by probability, and the act of observation itself shapes the phenomena we seek to understand. At its heart, the principle arises from the wave-like behavior of matter. Electrons and other particles do not exist as simple point-like objects, but as probability waves spread across space. Attempting to pin down a particle's exact position as a wave with a sharply defined peak. Yet a sharply defined wave in space demands a combination of many different momenta, making the particle's momentum highly uncertain. Conversely, a precise momentum corresponds to a long, evenly spread wave in space, leaving its position vague. These relationships are not just abstract concepts. They emerge naturally from the mathematics of quantum mechanics. They reveal a reality in which the very notions of location and motion are entwined in a delicate and inevitable trade-off. The principle is grounded in rigorous experimental evidence. The most direct demonstrations come from diffraction and interference experiments. When electrons pass through a narrow slit, their positions become constrained, but their momenta become dispersed, creating a spread in the resulting pattern on a detecting screen. Observations of photons, atoms, and even larger particles under controlled conditions consistently reflect this trade-off. Werner Heisenberg first formulated the principle theoretically in the 1920s. but subsequent experimental work has affirmed its universal character. Quantum uncertainty is not an artifact. It is woven into the fabric of reality, appearing whenever one probes the smallest scales. The implications of the uncertainty principle are profound and philosophically unsettling. In classical mechanics, the world is a vast clockwork in which knowing initial conditions allows precise predictions of the future. In the quantum realm, such determinism dissolves. Uncertainty does not merely limit knowledge, but imposes fundamental indeterminacy. Particles flicker between possibilities, and the universe is a stage for probabilities rather than certainties. The principle reshapes our understanding of causality, the flow of time, and the nature of reality itself. It suggests that at the smallest scales, the universe resists being fully captured by human observation, inviting a form of humility in the face of nature's complexity. Despite its abstract nature, the uncertainty principle has practical consequences. In quantum chemistry, it explains why electrons do not spiral into atomic nuclei, giving rise to the stability of matter. In modern technology, it underpins the operation of electron microscopes and the principles of quantum computing. It also informs the limits of precision in timekeeping, measurement, and sensing at atomic scales. Even in emerging fields like quantum cryptography, the principle guarantees security by making certain measurements inherently disruptive. What seems like a philosophical curiosity manifests in tangible and transformative ways in the world around us. Many misunderstandings surround the principle. It does not imply that humans cannot measure with sufficient skill, that nature itself imposes constraints. It is not about experimental imperfection, but about the impossibility of separating position from momentum in absolute terms. Nor does it mean that particles are fundamentally random in every respect. Rather, it describes an intrinsic link between complementary properties. Clarifying these subtleties reveals the principle as both precise and profound, a guide to the limits of knowledge, rather than a statement of chaos. In contemplating the Heisenberg uncertainty principle, one is drawn into the mystery of existence. It confronts us with the strangeness of the microscopic world and invites reflection on the relationship between observer and observed. The principle reminds us that reality is not a rigid edifice, but a living interplay of possibilities. In acknowledging this limitation, we glimpse a universe more intricate and awe-inspiring than intuition alone can reveal. Quantum uncertainty challenges the boundaries of thought and perception, leaving an enduring impression that certainty is fleeting and wonder is inexhaustible. The very act of seeking understanding becomes an encounter with the profound, and in that encounter, science and philosophy converge, revealing the universe as a place of perpetual marvel. Wave function. At its essence, the wave function is the mathematical embodiment of possibility, a representation of the universe's subtle whisperings before any observation. It is not a tangible object, not something we can touch or see in a conventional sense. Instead, it exists in the abstract domain of complex numbers and probabilities, describing every conceivable state a quantum system might occupy. Each particle, from the smallest electron to more intricate assemblies of matter, carries within it a wave function that encodes an entire spectrum of potential realities. It is a map not of what is, but of what could be, a tapestry woven from the threads of uncertainty. The way it works is both elegant and enigmatic. The wave function evolves smoothly according to the deterministic rules of the Schrödinger equation. Unlike the classical world, where an object has a definite position and velocity, a quantum system under the governance of a wave function exists in a superposition, a combination of multiple states simultaneously. The act of measurement does not reveal a hidden truth, so much as it interacts with this superposition, collapsing it into one of the many potential outcomes. The evolution of the wave function is continuous and predictable until an interaction occurs, at which point the universe offers a single reality from the vast field of possibilities. Evidence for the wave function is woven into the very experiments that revealed the quantum domain. The double-slit experiment shows us that particles like electrons exhibit interference patterns, as if each particle travels through multiple paths at once. These patterns can be predicted with precision only by using the wave function, highlighting its role as the underlying description of quantum behavior. Schrödinger's own thought experiment, the cat that exists in an oscillation between life and death until observed, illustrates the bizarre consequences of superposition. Moreover, the quantized energy levels of atoms, confirmed through spectral lines, reflect the probabilities dictated by the wave function rather than a simple classical trajectory. The implications of this are profoundly unsettling. It challenges the intuitive notions of reality and determinism that have guided human thought for centuries. A particle does not have a definitive position until it is measured, yet the wave function provides an almost divine precision in predicting the likelihood of finding it there. It suggests a universe where uncertainty is not a limitation of knowledge, but a fundamental feature of existence. The very idea that multiple outcomes can coexist, and that our act of observation selects among them, provokes questions about the role of consciousness, the nature of reality, and the boundaries between what is real and what is potential. Despite its abstraction, the wave function has concrete applications in the world we inhabit. It underpins the design of semiconductors, lasers, and quantum dots, technologies that are essential to modern electronics and communication. In chemistry, it allows us to predict molecular structures and reaction dynamics with astonishing accuracy. Quantum computing relies directly on the principles of superposition and entanglement, exploiting the wave function to perform calculations that would be unimaginable for classical computers. Even in medicine, techniques such as magnetic resonance imaging grounded in the precise understanding of quantum states. Yet misconceptions abound. Many imagine the wave function as a physical wave undulating through space, like water or sound, but it is a mathematical abstraction describing probabilities. Some conflate collapse with a mystical intervention, but it is a well-defined interaction governed by the rules of quantum mechanics. Others assume that the probabilistic nature of the wave function implies randomness in every facet of life, when in fact it is the microscopic domain where these principles dominate, leaving the macroscopic world mostly predictable. Ultimately, the wave function invites reflection on the nature of reality itself. It embodies both the limits of human intuition and the power of mathematics to reveal truths hidden from ordinary perception. To study it is to confront the delicate balance between certainty and ambiguity, to witness the dance of possibility that underlies the cosmos. In the quiet depths of these equations, one glimpses the extraordinary subtlety of existence, the intimate connection between observer and observed, and the profound wonder of a universe that is at once knowable and unfathomable. Identical particles. In the depths of the quantum world, there exists a category of entities that defy the ordinary sense of individuality. These are identical particles. Unlike objects in the macroscopic world, where each item can be distinguished by subtle differences, identical particles are fundamentally indistinguishable. No matter how closely one examines them, no label, no mark, no hidden trait can set one apart from another. Their existence challenges the notion of identity itself, forcing us to reconsider what it means for something to be the same as another. The concept extends beyond mere appearance into the very structure of reality, influencing the laws that govern the microscopic universe. The way these particles behave is unlike anything in everyday life. They adhere to strict statistical rules, dictated by their intrinsic nature. Fermions, such as electrons, obey the Pauli exclusion principle, which forbids any two from occupying the same quantum state simultaneously. This simple rule, invisible yet absolute, sculpts the architecture of matter, ensuring stability and structure in atoms and molecules. Bosons, in contrast, are allowed to congregate in the same state, a behavior that permits phenomena like superconductivity and laser light. The quantum symmetries and constraints that govern identical particles are precise and unyielding, creating patterns of behavior that are simultaneously abstract and extraordinarily concrete. Evidence of their peculiar nature emerges from experiments that probe the limits of observation. The double-slit experiment, when conducted with electrons, reveals interference patterns that betray their wave-like identity and the indistinguishability of each particle. In atomic spectroscopy, the discrete energy levels of electrons arise from the requirement that no two fermions share the same state. Bose-Einstein condensation, observed at temperatures near absolute zero, demonstrates the collective behavior of bosons as they coalesce into a single quantum state. These experiments not only confirm theoretical predictions, but also expose a universe far more enigmatic than classical intuition allows. The implications of identical particles are profound and subtly unsettling. They strip away the notion that all matter can be uniquely tagged and categorized. They reveal a cosmos in which individuality is not a universal principle but a rare exception. At the smallest scales, reality is a fabric woven from indistinguishable threads, each particle existing as a reflection of others. This challenges our perception of identity and separateness, suggesting that at a fundamental level, the world is governed by patterns and symmetries rather than by singular objects. Despite their abstraction, identical particles are central to the material and technological world. The stability of matter itself depends on fermions occupying distinct states, while bosons enable technologies that exploit collective quantum effects. Semiconductors, lasers, and superconducting materials all rely on the principles that emerge from these indistinguishable entities. Even chemical bonding, the foundation of biology and life, is a direct consequence of the rules governing identical particles. In this way, what seems purely theoretical becomes essential to the tangible reality surrounding us. Yet misconceptions abound. It is sometimes assumed that identical particles are simply similar, like coins from the same mint. In truth, their indistinguishability is intrinsic and absolute. Another misunderstanding that this property only matters in esoteric physics laboratories. In reality, it shapes the architecture of the universe, from the structure of atoms to the behavior of stars. Finally, there is the intuitive but misleading belief that particles retain identity across time and space. Quantum mechanics insists otherwise, insisting on a radical rethinking of individuality that is counterintuitive but empirically undeniable. In contemplating identical particles, one encounters a profound philosophical reflection on the nature of being. They are the reminder that at the most elemental level, the universe does not mirror human notions of uniqueness or separateness. Matter, energy, and existence are bound by symmetries and indistinguishable repetition, patterns that evoke both wonder and humility. The reality of identical particles challenges us to embrace a vision of the cosmos, where identity is fluid, where the boundaries between entities blur, and where the ordinary rules of the everyday dissolve into a realm of extraordinary subtlety. In acknowledging their existence, we glimpse a deeper coherence, an elegant and austere order underlying all that is, and are invited to marvel at a universe where sameness and difference coexist in a harmony beyond comprehension. Quantum spin. Quantum spin is a fundamental property of particles that defies classical intuition. Unlike everyday spinning objects, it is not a literal rotation, but an intrinsic form of angular momentum that particles possess naturally. Every electron, proton, and neutron carries spin, and it is quantized, meaning it exists in discrete values rather than a continuous range. This intrinsic characteristic shapes the very fabric of matter and the interactions that govern the microscopic universe. It is a concept that challenges our perception of reality, inviting contemplation of the strange rules that govern the subatomic world. At its core, spin emerges from the mathematics of quantum mechanics. It is described by spin operators and wave functions, which obey specific commutation relations. The spin of a particle determines how it responds to magnetic fields and interaction captured by the Pauli spin matrices for electrons. When measured along a chosen axis, spin can take on only certain allowed values, such as up or down, for spin 1/2 particles. This binary outcome reflects the underlying probabilistic nature of quantum mechanics, where certainty exists not in the properties themselves, but in the likelihood of observing them. The quantization of spin also leads to the unique symmetry properties of particles, distinguishing fermions from bosons and dictating the structure of matter on a fundamental level. The existence of spin was not immediately apparent, but became evident through experiments that revealed its profound effects. The Stern-Gerlach experiment provided early, clear evidence by sending silver atoms through a non-uniform magnetic field and observing their deflection into discrete spots. This splitting of atomic beams could not be explained by classical angular momentum alone. Later experiments, such as those involving electron spin resonance, confirmed the precise behavior of spin in magnetic fields and allowed researchers to probe its interactions in unprecedented detail. Each of these investigations provided glimpses into a hidden order, a reality where the smallest constituents of matter exhibit behavior that is both predictable and yet profoundly counterintuitive. Spin carries implications that extend beyond mere physics and into the realm of philosophical reflection. It is a property that exists without a classical analog, a reminder that nature does not conform to our macroscopic intuitions. Particles with spin exhibit behaviors that challenge the notions of individuality and separability. Entanglement, closely linked to spin correlations, demonstrates that the state of one particle can instantaneously influence another, regardless of distance. This non-locality undermines conventional ideas of causality and locality, inviting contemplation of a universe in which the boundaries between entities are far more subtle than everyday experience suggests. The practical impact of spin is substantial, shaping technologies that touch everyday life. Magnetic resonance imaging relies on the alignment and manipulation of nuclear spins to generate detailed images of the human body. Spintronics exploits the spin of electrons to create faster, more efficient electronic devices that go beyond the capabilities of traditional charge-based circuits. Quantum computing leverages spin states as qubits, allowing computations that surpass classical limits by harnessing superposition and entanglement. In each of these applications, the abstract, seemingly esoteric property of spin becomes a tangible tool, a bridge between the philosophical depth of quantum mechanics and the practical demands of modern technology. Despite its centrality, spin is frequently misunderstood. It is often imagined as a miniature top spinning on its axis, a notion that can mislead rather than illuminate. Spin is not a literal rotation and does not involve any spatial motion in the classical sense. Another common misconception is that spin values indicate size or shape. Instead, they represent an intrinsic form of angular momentum, a quantum label with no direct visual analog. These misunderstandings underscore the difficulty of translating quantum phenomena into human intuition, where analogies can be both helpful and limiting. Ultimately, quantum spin invites reflection on the nature of reality itself. It challenges us to consider a world where intrinsic properties govern behavior in ways that are invisible, counterintuitive, and deeply interconnected. Spin is a reminder that at the foundation of the universe, simplicity and complexity coexist in a delicate balance, and that the seemingly ordinary particles of matter carry within them the extraordinary rules of quantum existence. It is both a scientific truth and a philosophical prompt, urging an appreciation for the subtle, enigmatic structures that underlay everything we observe and experience. Qubits. In the quiet depths of quantum theory, the qubit emerges as a concept both elegant and perplexing. Unlike the classical bit, which exists decisively as either 0 or 1, a qubit embodies a state of potentiality, hovering in a liminal space between certainty and ambiguity. It is a quantum particle, or often a carefully prepared atom, photon, or electron, whose information is encoded in subtle properties such as spin or polarization. In contemplating a qubit, one confronts the very nature of information at the edge of human understanding. It is not merely a carrier of data, but a window into the strange architecture of reality itself. The mechanics of a qubit defy intuition. In classical computation, the bit is immutable, confined to the strict dichotomy of on or off. A qubit, however, resides in superposition, an ethereal blend of 0 and 1, described mathematically as a linear combination of both states. Observation collapses this state into a definitive outcome, but prior to measurement, the qubit exists as a spectrum of possibilities. This fragile dance is governed by the laws of quantum mechanics, where entanglement allows qubits to form intricate correlations that transcend classical logic. Two entangled qubits become mirrors of each other, their states intertwined regardless of distance, hinting at a universe more interconnected than our senses can apprehend. Manipulating qubits requires exquisite precision, for even the faintest disturbance can irreversibly alter their delicate state. Evidence for the qubit and its peculiar behavior has accumulated through experiments that are as beautiful as they are confounding. One of the most profound demonstrations is the double-slit experiment with single photons or electrons, revealing interference patterns that betray the particles' interference with themselves in superposition. More sophisticated tests involve superconducting circuits or trapped ions, where scientists observe coherent oscillations and entanglement over measurable durations. Each experiment serves not merely as proof of a hypothesis, but as a philosophical meditation on reality. The qubit is no abstraction. It is tangible, yet it challenges our assumptions about locality, determinism, and causality. The implications of qubits are deeply unsettling and endlessly fascinating. They suggest a reality that is probabilistic at its core, where observation shapes existence and separability is an illusion. Information is no longer a static entity, but a dynamic interplay of possibilities. The qubit forces a reconsideration of what it means to know, to measure, to predict. In its behavior lies a mirror to our own consciousness, hinting at layers of reality where certainty is an emergent property rather than an inherent one. It is in this tension between potential and actual that the qubit is most profoundly weird, embodying a form of knowledge that defies everyday logic. Yet the qubit is not confined to philosophical rumination. Its peculiarities have tangible applications that promise to reshape technology. Quantum computers leverage superposition and entanglement to solve problems that are intractable for classical machines, from factoring immense numbers to simulating complex molecules. Quantum cryptography uses the sensitivity of qubits to detect eavesdropping, creating communication channels of unprecedented security. Even in the realm of sensing and metrology, qubits provide unmatched precision, offering insights into the fabric of space, time, and energy. The potential is vast, and humanity stands at the threshold of a new computational paradigm. Despite fascination, qubits are often misunderstood. They are not simultaneously 0 and 1 in the simplistic sense. Superposition is a nuanced mathematical state, not a casual ambiguity. Entanglement is not telepathy, but a correlation defined by quantum laws. Qubits do not violate physics, they reveal its subtleties. Misconceptions arise from translating their behavior into human intuition, yet the challenge is to appreciate their strangeness without forcing them into familiar categories. In reflecting upon the qubit, one encounters the profound intersection of science and philosophy. It is a reminder that reality does not conform to everyday expectation, and that understanding requires humility and patience. The qubit embodies potential, fragility, and connection, urging us to reconsider the limits of knowledge and computation. In contemplating it, we glimpse the poetry of the universe, where uncertainty is not a flaw, but an essential feature. The qubit is a beacon, guiding thought through the intricate dance of probability and possibility, illuminating the deep mystery at the heart of existence. Quantum computing speed. In the quiet corridors of thought, where the boundaries of possibility stretch beyond classical intuition, quantum computing speed emerges as a strange and compelling phenomenon. At its heart lies the radical departure from the linearity that governs traditional computation. Classical computers, with their binary foundations, advance through calculations step by step, each bit holding a single truth. Quantum computers, in contrast, embrace a multiplicity of truths simultaneously. The concept is as elegant as it is confounding. A qubit can inhabit a state of 0 and 1 at once, weaving a tapestry of potential outcomes that unfolds in parallel. The speed of quantum computing is not merely a measure of clock cycles or transistor density. It is a manifestation of this superpositional liberty, a dance of probabilities that compresses vast computational landscapes into moments that defy ordinary perception. The workings of this speed derive from principles that seem plucked from philosophical musing as much as from physics. Superposition allows qubits to explore many possibilities simultaneously, while entanglement binds them across space in correlations that appear instantaneous. Interference acts as a subtle arbiter, amplifying the paths that lead to correct solutions and cancelling those that do not. Within this delicate choreography, computation becomes an exercise in guiding probability towards certainty. It is a universe of calculation where parallelism is not a convenience, but a necessity, where time is bent by the underlying logic of quantum amplitudes. Understanding this is to recognize that the speed of quantum computing is not just about doing things faster. It is about reconceptualizing what it means to solve a problem at all. Evidence of this astonishing capability has begun to emerge through carefully orchestrated experiments. Researchers have demonstrated quantum supremacy in specific tasks, performing calculations in seconds that would challenge the most powerful classical supercomputers for millennia. These experiments are both technical triumphs and philosophical provocations. They reveal that the constraints we once assumed to be absolute may be malleable, subject to the strange architecture of the quantum world. Each experiment is a step into an unfamiliar terrain where intuition falters, and yet clarity appears in the patterns that the qubits reveal. The speed at which quantum machines operate is not simply a triumph of engineering. It is a glimpse into an underlying logic of the cosmos that operates on principles both beautiful and alien. The implications of this speed touch upon the very nature of knowledge and computation. It challenges our notions of efficiency, of what can be known and how quickly. Problems that were once intractable may succumb to the subtle orchestration of quantum logic. Yet there is a strangeness inherent in this progress. The outcomes are probabilistic, never absolute until measured, leaving a sense of uncertainty entwined with mastery. The universe appears at once noble and elusive, offering glimpses of truth through pathways that classical thinking could scarcely anticipate. The philosophical resonance is profound. Speed here is not just acceleration, but an invitation to reconsider causality, determinism, and the texture of reality itself. Applications of this speed are already inspiring visions of the future. Cryptography, materials science, and complex optimization stand to be transformed by calculations performed in moments rather than eons. Chemical simulations that once demanded prohibitive resources may become routine, potentially reshaping medicine and energy. Artificial intelligence could leverage quantum acceleration to explore vast solution spaces, yielding insights beyond the reach of conventional machines. Even so, these applications are nascent, promising potential rather than immediate revolution. The allure lies in the philosophical suggestion that nature itself may be harnessed in ways that honor its own complexity, revealing efficiencies hidden within the very fabric of reality. Common misconceptions persist as the mind struggles to reconcile the speed of quantum computing with classical expectation. It is not magic, nor omnipotent calculation. Quantum computers do not instantly solve every problem. They excel in specific domains where parallelism and interference can be exploited. Nor does their speed imply a limitless future. Decoherence and error remain stubborn companions. Yet these limitations only deepen the fascination, for they illustrate that the universe has a rhythm, and quantum speed is a dance within that rhythm, not a breach of natural law. In closing, quantum computing speed is a mirror held up to the subtlety of the cosmos. It is a phenomenon that invites awe, a testament to the ingenuity of human thought and the strange generosity of the quantum world. In its rapid computation, there is a meditation on time, on possibility, and on the nature of understanding itself. To contemplate it is to stand at the threshold of a new cognitive horizon, where speed is measured not merely in seconds, but in the unfolding of insight across the dimensions of reality. Double-slit experiment. The double-slit experiment is a profound demonstration of the strange nature of reality, a window into the behavior of matter and light that challenges our deepest intuitions. At its core, it is a simple arrangement. A source emits particles or waves toward a barrier with two narrow openings. Beyond the barrier lies a detection screen where the outcomes of these emissions are recorded. What unfolds is far from ordinary, revealing patterns that defy classical logic and demand contemplation of the fundamental principles of the universe. In execution, the experiment begins with particles, such as electrons or photons, directed at the barrier containing two slits. If one slit is covered, the particles produce a pattern consistent with discrete impacts, like tiny marbles striking a surface. Yet, when both slits are open, the pattern on the screen transforms into an interference pattern, characterized by alternating bands of light and dark, peaks and troughs, as if the particles behave simultaneously, waves spreading through both slits at once. Remarkably, this wave-like interference emerges even when particles are sent one at a time, suggesting that each particle traverses multiple paths in a manner that defies classical understanding. The act of observation further complicates matters. When a measurement device is placed to determine through which slit a particle passes, the interference pattern collapses, and the particles behave as if they choose a single path, yielding to simple clusters corresponding to the slits. This duality is not merely a curiosity, but a revelation that observation and measurement intertwine with the fundamental behavior of reality. The experimental evidence that grounds these conclusions has been amassed over decades, beginning with Thomas Young's demonstration of light interference in the early 19th century. Later experiments, refined by quantum physicists, have extended the observations to individual electrons, neutrons, and even larger molecules. Each repetition of the experiment reinforces the enigmatic result. Particles do not simply occupy a single trajectory, but exhibit a probabilistic superposition, only resolving into a definitive state upon observation. The meticulous repetition of these experiments, under controlled conditions, lends an air of incontrovertible truth to the counterintuitive behavior they reveal, forcing a reconsideration of the classical boundaries between matter, energy, and consciousness. The implications are profound and unsettling. The experiment confronts us with the dual nature of reality, where objects possess both wave-like and particle-like characteristics, and where the act of measurement appears to play an active role in shaping outcomes. It challenges the notion of an objective universe existing independently of observers, suggesting that reality at its most fundamental level, intertwined with information, observation, and potentiality. It raises philosophical questions about the nature of existence itself, whether the world possesses definite properties when unobserved, and how our perception may participate in the unfolding of physical phenomena. Despite its abstract nature, the double-slit experiment has practical consequences. It underlies the principles of quantum computing, where superposition and interference enable computations far beyond the reach of classical systems. It informs the development of advanced imaging techniques, quantum encryption, and sensors of extraordinary precision. The strange behavior of particles, once considered purely theoretical, now informs technologies that promise to transform communication, computation, and measurement in ways that were inconceivable before the quantum era. Common misunderstandings abound. Some assume the experiment implies that consciousness alone alters reality, a leap that oversimplifies the nuanced interplay of measurement and physical systems. Others interpret the interference pattern as evidence of particles splitting in two, a misconception that misrepresents the probabilistic and non-local nature of quantum mechanics. The results are subtle and mathematically precise, not mystical, and demand careful interpretation to avoid exaggeration or distortion of their meaning. In closing, the double-slit experiment is a mirror held to the deepest structures of existence. It invites awe, reflection, and humility, reminding us that the universe operates in ways both intelligible and profoundly mysterious. It challenges the boundaries of observation, the meaning of reality, and the limits of human intuition. As we continue to probe, measure, and experiment, we are confronted not only with the peculiar behavior of particles, but with the nature of our own inquiry, the role of knowledge, and the ever-unfolding dialogue between observer and observed. In its simplicity and elegance, the double-slit experiment exemplifies the philosophical wonder of science, revealing a world more intricate and enigmatic than our classical minds can easily grasp. Quantum teleportation. Quantum teleportation is a process that seems to defy the conventional limits of distance and information transfer. At its core, it involves transmitting the exact state of a quantum particle from one location to another without physically moving the particle itself. This is not the teleportation of matter, as imagined in science fiction, but the faithful transfer of information that describes a particle's quantum state. It rests on the peculiar and deeply counterintuitive principles of quantum mechanics, where entanglement and superposition govern the behavior of particles in ways that challenge our classical understanding of reality. The mechanism behind quantum teleportation is on the phenomenon of entanglement, a link between two or more particles, such that the state of one instantaneously influences the state of another, regardless of the distance separating them. To teleport a quantum state, an entangled pair of particles is first prepared, one at the sender's location and the other at the receiver's. The sender then performs a joint measurement on the particle to be teleported and their half of the entangled pair, a measurement that simultaneously alters the state of the receiver's particle in a predictable way. The outcome of this measurement is classical information, which must be transmitted through conventional means. Once received, it allows the receiver to apply a specific transformation to their particle, reproducing the original quantum state perfectly. The elegance of this process lies in its subtle blend of classical communication and quantum correlation, creating a bridge across space without physically traversing it. The journey from theory to proof was paved by meticulous experimentation. In 1997, the first successful demonstration of quantum teleportation was achieved by a team of physicists who teleported the state of a photon across several meters. Photons, with their fragile quantum states, were ideal candidates, and the experiment confirmed that the quantum information could be transmitted with complete fidelity. Since then, teleportation has been extended to atoms and ions, with distances stretching from laboratory benches to kilometers of optical fiber. Each successful experiment reinforced the concept that quantum states could exist, move, and be manipulated in ways that conventional intuition cannot grasp. Quantum teleportation challenges not just our technical understanding, but our philosophical conception of reality. It underscores the non-locality of the universe, where particles separated by vast distances remain linked in ways that seem instantaneous. The process illustrates that information and matter are distinct in the quantum world, a separation that feels almost mystical. It also raises questions about identity and continuity, since the original state is destroyed in the act of teleportation, leaving a perfect copy in its place. Such ideas invite contemplation on the nature of existence, on what it means for a property to be real if it can exist into locations sequentially, without traversing the intervening space. Despite its conceptual oddity, quantum teleportation has practical applications that could reshape technology. It is central to the development of quantum networks, where information can be transmitted securely across continents with absolute immunity to eavesdropping. This capability promises the foundation for a quantum internet, enabling computations and communications beyond the reach of classical devices. Additionally, it offers pathways for distributed quantum computing, where entangled nodes process information collectively, amplifying computational power in ways unimaginable with conventional systems. Yet, the concept is often misunderstood. Many imagine teleportation as the movement of matter or the instantaneous transport of people. In reality, quantum teleportation transfers only the information that defines a particle's state, not the particle itself. It cannot circumvent the speed of light for information transfer, since classical communication is required. Its mystique lies in the transformation of states, rather than objects, a subtlety that is frequently lost in popular depictions. Ultimately, quantum teleportation is both a triumph of human ingenuity and a reminder of the universe's strangeness. It illustrates the power of abstract thought married to experimental precision, revealing a cosmos more interconnected than the senses alone can perceive. As we delve deeper into the principles that make such phenomena possible, we glimpse a reality where information transcends location, where the fabric of existence is more malleable than our minds can fully embrace. It is a testament to the beauty of science that we can explore these realms, that we can understand and manipulate the very essence of matter and information, and that in doing so, we are compelled to reconsider the boundaries of what is possible. Virtual particles. Virtual particles are entities that exist fleetingly within the quantum fabric of reality. They are not particles in the conventional sense, for they do not possess a permanent, observable presence. Instead, they appear spontaneously in the vacuum of space, manifesting and vanishing in intervals so brief that their existence is imperceptible to direct measurement. They inhabit a world governed by uncertainty, where the classical notions of position and momentum dissolve into probability and fluctuation. In contemplating virtual particles, one confronts a realm where the boundaries between nothingness and something are fragile and fluid, where the vacuum itself hums with ephemeral activity. Their workings emerge from the principles of quantum field theory, where each field permeates the universe and can ripple with energy. These ripples are the virtual particles, arising as temporary excitations that enable interactions between real particles. When two electrons repel each other, they do so not merely by contact, but by exchanging virtual photons, carriers of the electromagnetic force that exist only for a transient heartbeat. The mathematics of these interactions is subtle, relying on complex diagrams and integrals that capture the fleeting influence of these unseen actors. They do not obey the constraints of classical energy conservation in the ordinary sense, but are allowed to exist within the limits of uncertainty for such brief spans that their effects are nevertheless measurable and essential to the universe's structure. Experimental evidence for virtual particles is indirect but compelling. The Casimir effect demonstrates a force between two uncharged plates in a vacuum, a phenomenon arising precisely because virtual particles populate the space between them differently than the surrounding void. High-energy particle experiments also reveal their presence in the corrections needed to predict particle behavior accurately, showing that even though they cannot be observed directly, their fingerprints appear in the patterns of scattering and decay. These experimental confirmations illuminate a paradoxical truth. Something can be undeniably real even when it is never directly seen, challenging the way we define existence. The implications of virtual particles invite a sense of philosophical awe. They suggest that emptiness is never truly empty, that the vacuum seethes with transient life, and that reality itself is a continuous dialogue between potentiality and manifestation. This ephemeral dance blurs the line between existence and non-existence, prompting questions about the nature of reality and the limits of human perception. The notion that forces between matter are mediated by entities that exist only momentarily provokes a sense of the uncanny, a recognition that the universe operates on levels far removed from ordinary experience. Despite their fleeting nature, virtual particles have tangible consequences. They influence the behavior of atoms, contribute to the mass of particles through interactions with fields, and underpin effects that drive advanced technologies. Understanding these entities has informed the development of quantum electrodynamics, the design of particle accelerators, and the precision of atomic clocks. In contemplating them, scientists navigate not only the theoretical landscapes of fields and interactions, but also the practical avenues through which quantum mechanics shapes our world. Common misconceptions about virtual particles abound. They are sometimes imagined as tiny dots flitting about like fireflies, but such images betray the subtleties of their existence. They do not exist in space in the conventional sense, cannot be captured, and cannot be observed directly. Their presence is inferred through their influence, a reminder that in the quantum world, the effects of reality can precede our ability to see it. This distinction is crucial for a proper understanding of their role, for they are as much a feature of the mathematical description of the universe as they are of physical phenomena. In closing, virtual particles are a window into the enigmatic depths of the universe. They reveal a cosmos alive with transient phenomena, governed by principles that defy ordinary intuition. Contemplating them invites a recognition that reality is layered, that existence is not a simple matter of being, but a complex interplay of energy, potential, and ephemeral form. They are reminders that the universe is far stranger and more intricate than our everyday experiences suggest, and that the journey to comprehend it requires both rigor and imagination, humility and wonder. Quantum explanation of chemical bonds. Chemical bonds are the invisible threads that weave atoms into the tangible world around us. They are the silent architects of molecules, dictating shapes, behaviors, and the very essence of matter. At first glance, a bond might seem a simple attraction, a magnetism between elements, yet at the quantum level, it reveals an intricate dance governed by principles that defy ordinary perception. Understanding chemical bonds through quantum mechanics is not merely an exercise in abstraction. It is an invitation to peer into the fundamental rules that govern reality. At its core, a chemical bond is a manifestation of the interactions between electrons and nuclei. Electrons occupy regions of space called orbitals, and when atoms approach each other, these orbitals can overlap. This overlap allows electrons to be shared or transferred in ways that lower the overall energy of the system. Covalent bonds arise when electrons are shared between atoms, forming a stabilized region of electron density between nuclei. Ionic bonds emerge when electrons are transferred from one atom to another, creating a balance of positive and negative charges that hold the atoms together. These bonds are not static connections, but dynamic outcomes of the quantum behavior of electrons. The mechanics behind this phenomenon on the principles of quantum theory. Electrons do not traverse fixed paths, but exist as probability clouds, their positions described by wave functions. The formation of a bond corresponds to a change in the shape and energy of these wave functions, creating states where the likelihood of electrons existing between nuclei is maximized. Pauli's exclusion principle ensures that electrons occupy distinct quantum states, shaping the geometry of molecules. Schrödinger's equation, solved for simple systems, predicts the energy levels and configurations of electrons in bonds. At this microscopic level, bonding is an energetic compromise, a balance of attraction and repulsion that quantum mechanics alone can fully describe. Experimental evidence has confirmed these theoretical insights. Spectroscopic techniques reveal energy transitions that correspond to the quantized states of electrons within bonds. X-ray diffraction uncovers the precise arrangements of atoms in crystals, revealing patterns that match quantum predictions. The photoelectron effect allows scientists to probe the energies of electrons, showing the discrete levels predicted by quantum models. Together, these observations provide a consistent picture. Bonds are not arbitrary forces, but quantifiable phenomena arising from the probabilistic nature of electrons. The quantum perspective of chemical bonds carries implications that challenge intuition. Electrons behave simultaneously as particles and waves, and bonds are born from this duality. A single electron can influence the structure of an entire molecule without a classical counterpart. The notion of resonance, where a molecule exists as a hybrid of multiple structures, defies the simple idea of fixed connections. Bonds can stretch, bend, and even break in ways that classical mechanics cannot predict. This unpredictability at the foundational level of matter invites a contemplative humility, a recognition that the familiar solidity of objects is an emergent property of underlying uncertainties. These insights have practical ramifications in the material and biological sciences. The stability of DNA, the reactivity of enzymes, the conductivity of materials, and the design of pharmaceuticals all hinge on a quantum understanding of bonding. Quantum chemistry allows researchers to predict how molecules will interact before they are synthesized, guiding the development of new materials and drugs. Catalysis, semiconductor design, and nanotechnology all rely on manipulating bonds with a precision born from quantum insight. The tangible world, from the smallest protein to the most complex alloy, is constructed through the language of quantum mechanics. Despite its explanatory power, common misconceptions abound. Bonds are often imagined as rigid sticks connecting atoms or simple electrostatic attractions. Electrons are sometimes pictured as tiny planets orbiting a nucleus, ignoring their wave-like nature. Covalent and ionic bonds are sometimes seen as entirely separate phenomena, when in reality they exist on a spectrum of electron sharing and transfer. Recognizing the fluid, probabilistic nature of bonding is essential to truly grasp the elegance of the quantum world. Ultimately, chemical bonds reveal the profound beauty of existence at the smallest scales. They are the rules by which matter organizes itself, the quiet forces shaping life and the universe. Quantum mechanics transforms our understanding from simple attraction to a deeply intricate interplay of probability, energy, and symmetry. Contemplating these bonds invites a sense of awe, a reflection on the extraordinary coherence of the world at its most fundamental level, and a recognition that the fabric of reality is woven not with certainty, but with the subtle patterns of possibility. Photons. Light and energy manifest in the universe as photons. They are the fundamental particles of electromagnetic radiation, carriers of light, yet they defy simple categorization. Neither purely particle nor purely wave, photons exist in a state that challenges our classical intuitions about reality. To consider a photon is to consider the essence of how the universe communicates energy across the vast emptiness of space, traveling relentlessly at the ultimate speed limit, indifferent to time in the manner that matter experiences it. Each photon embodies a discrete quantum of energy, a perfect unit that cannot be divided, yet collectively they produce the continuous flow of light that shapes our perception of the world. The behavior of photons is a window into the strange architecture of the quantum world. They move in waves, displaying interference and diffraction, patterns that reveal a subtle underlying order. Yet, when observed as individual particles, they impact surfaces discretely, like drops of light striking a detector one at a time. This dual nature exposes the limitations of classical physics and invites contemplation about the very nature of existence. Their emission, absorption, and scattering follow precise probabilities, governed by the mathematics of quantum electrodynamics. Yet within that predictability, there remains a profound mystery about the exact path or fate of any single photon. Evidence of photons emerges through experiments that have illuminated the invisible. The photoelectric effect demonstrated that light can knock electrons free from metal surfaces, a phenomenon that could only be explained if light were composed of quantized particles carrying specific energy. Double-slit experiments further revealed their paradoxical character, producing interference patterns even when photons travel individually, as if each particle carries with it a memory of all possible paths it might take. Such experiments do not merely confirm theories. They evoke a sense of wonder about the subtle and intangible ways the universe operates, bridging the gap between abstract mathematics and tangible phenomena. The implications of photon behavior are both profound and unsettling. Time and space, energy and matter, all interact through these minuscule carriers of light, suggesting a universe where observation and reality are intimately entwined. A photon does not experience time in the human sense. Its journey from the heart of a distant star to our eyes is instantaneous from its perspective, yet spans eons in hours. They also reveal the limitations of perception and certainty. Their existence challenges assumptions about continuity and locality, provoking questions about what it means to observe, to measure, and to know. In practical terms, photons are indispensable to modern life. They carry information through fiber optic cables, enabling instantaneous global communication. They power solar cells, converting sunlight into electricity with elegant efficiency. They allow us to probe the cosmos through telescopes, capture fleeting moments in photography, and explore matter at the atomic scale with lasers. Each application relies on both the particle and wave aspects, leveraging their strange nature to transform technology, medicine, and exploration. Without photons, the framework of modern civilization would be unrecognizable, and yet their presence remains nearly invisible, subtly shaping experience and knowledge. Misconceptions about photons abound. They are often imagined as tiny balls of light, traveling along defined paths, but such a notion is misleading. Photons have no rest mass and do not behave like classical projectiles. Their energy depends on frequency rather than size or speed. They do not slow down in empty space and do not possess a color inherent to themselves. The color is an emergent property of interaction with matter. Furthermore, they cannot be contained in the way objects with mass can. They exist in states defined by probability until they interact. These subtleties are crucial for understanding both the physics of light and the philosophical implications of a reality that is stranger than intuition allows. Ultimately, photons compel reflection on the interplay between reality and perception. They are a reminder that the universe is not simply a backdrop for a human experience, but an intricate web of interaction, energy, and probability. To study photons is to engage with the fundamental principles that govern existence, to confront the delicate balance between determinism and uncertainty, and to marvel at the elegance with which the cosmos conveys energy across the void. In their fleeting, luminous journeys, photons carry not only light, but the profound mystery of the universe itself. Lasers. A laser is a device that produces a focused beam of light characterized by coherence, monochromaticity, and directionality. Unlike ordinary light that spreads and varies in wavelength, the light of a laser moves in precise alignment and uniform frequency. It represents an extraordinary convergence of physics and engineering, where the abstract principles of quantum mechanics manifest in a tangible, visible phenomenon. The very concept challenges our intuitive understanding of light, prompting reflection on the subtle relationship between energy, matter, and the human ability to manipulate nature with precision. The process by which a laser works is rooted in the interaction between photons and atoms. When atoms are excited to higher energy states, they can release energy in the form of photons. If a photon of a specific wavelength passes near an excited atom, it can stimulate the emission of an identical photon, resulting in a cascading effect of coherent light. This chain reaction occurs within a medium that may be a gas, liquid, or solid, enclosed by mirrors that reflect and amplify the light until it escapes as a concentrated beam. The precision of this process is remarkable, suggesting that light can be not merely observed, but sculpted according to the intentions of those who understand its fundamental rules. Historical experiments provide a concrete anchor to this abstract idea. The work of Theodore Maiman in 1960 with a ruby crystal marked the first demonstration of a functioning laser. Prior theoretical predictions by Albert Einstein at the foundation through the concept of stimulated emission. But the realization in a laboratory was a moment of profound significance. Observers at the time reported a fascination with the stark brilliance and focus of the emitted light, a sharp contrast to diffuse illumination. This experiment not only confirmed the theoretical underpinnings of coherent light, but also transformed scientific imagination, hinting at applications far beyond conventional optics. The implications of lasers extend beyond mere technological utility, touching the philosophical and the mysterious. Light that can be concentrated into a single beam challenges perceptions of space and distance, of intensity and subtlety. It forces contemplation of the interplay between natural laws and human ingenuity. The phenomenon of coherence itself is strange, revealing a level of order that contrasts with the randomness of ordinary light. In a broader sense, lasers embody the human pursuit of mastery over the fundamental forces of nature, a pursuit that is at once practical and profoundly contemplative. In the real world, lasers have permeated nearly every aspect of modern life. They guide surgical procedures with extraordinary precision, allow for the reading of information from compact disks, facilitate communication through fiber optics, and even probe distant galaxies. In manufacturing, they cut, weld, and measure with a delicacy that defies intuition. The utility of lasers seems to emerge from their simplicity of principle yet complexity of application, transforming abstract physics into tools that extend human capability. Each application underscores a bridge between understanding and effect, between theory and tangible impact. Common misconceptions about lasers reveal both their cultural mystique and the limits of public understanding. Many assume that lasers are inherently dangerous or exceptionally powerful in all contexts. In truth, a laser's potential for harm or utility depends entirely on its design and intensity. Others imagine that laser light is fundamentally different from ordinary light, when in fact it is ordinary light organized in an extraordinary way. These misconceptions hint at the tension between the remarkable qualities of lasers and the everyday intuition about light, emphasizing the gap between scientific comprehension and common perception. In conclusion, lasers are not merely tools, but a reflection of human curiosity and intellect. They are an elegant demonstration of the precision with which nature can be understood and harnessed. They reveal the subtle beauty of physics in action and the profound consequences of applying abstract theory to the material world. To witness a laser beam is to glimpse a universe where light itself can be tamed, directed, and intensified, offering both practical power and a source of contemplation. In this way, lasers occupy a space between art and science, between observation and intervention, standing as a testament to the human mind's capacity to engage deeply with the fabric of reality. Blackbody radiation. Blackbody radiation is a phenomenon that sits at the intersection of physics, philosophy, and the awe of the unseen. It is the emission of light and other forms of electromagnetic radiation by an idealized object that absorbs all incident radiation without reflection. Such an object, in its simplicity, becomes a perfect mirror of energy, radiating according to its temperature. It is not merely a concept confined to textbooks. It is a lens through which we glimpse the fundamental rhythm of the universe, the invisible dance of atoms and waves that orchestrates the energy surrounding us. At the heart of blackbody radiation is a delicate balance, a constant interplay between absorption and emission. When an object is heated, its atoms vibrate with increasing intensity, creating a spectrum of radiation. The hotter the object, the more its spectrum shifts towards shorter wavelengths, eventually reaching a point where visible light emerges. This relationship between temperature and emitted radiation is precise and predictable, yet it reveals a hidden complexity in the behavior of matter. It is a reminder that even the simplest seeming phenomena conceal layers of depth, layers that require careful observation and mathematical rigor to unravel. The history of blackbody radiation is entwined with some of the most profound experiments in physics. Wilhelm Wien and later Max Planck meticulously measured the spectrum of light emitted by heated bodies. Their work revealed a peculiar pattern that classical physics could not explain. The ultraviolet catastrophe, a term that haunts the origins of quantum theory, exposed the failure of existing laws. Classical equations predicted an infinite amount of energy at short wavelengths, a nonsensical result that begged for a new understanding. It was Planck who introduced a revolutionary idea. Energy is quantized, emitted in discrete packets called quanta. This insight did not merely solve a technical problem. It demanded a rethinking of reality itself, challenging the continuity of nature as it had been assumed. The implications of blackbody radiation extend far beyond laboratory experiments. It forced physicists to confront the limits of classical mechanics and open the door to quantum theory. The notion that energy comes in quantized units feels almost mystical, a glimpse into the granularity underlying the apparent smoothness of the world. It is strange and beautiful that an object as ordinary as a heated metal rod can expose such profound truths, that from the predictable glow of a filament emerges a philosophical revelation about the fabric of existence. The universe is not an infinite continuum, it is punctuated, discrete, and in that discreteness lies a hidden harmony. Blackbody radiation has practical consequences that touch everyday life. It governs the warmth of the sun and the color of stars, allowing astronomers to determine their temperatures and compositions. It informs the design of thermal cameras, incandescent lamps, and infrared heaters, shaping technologies that quietly surround us. Even in the microscopic realm, blackbody principles influence semiconductor design and the creation of highly sensitive detectors that probe the cosmos. What begins as a theoretical curiosity becomes a tool for understanding and harnessing the universe, a bridge from abstraction to tangible utility. Yet misconceptions abound. It is often assumed that blackbody radiation refers only to visible light, but it encompasses the entire electromagnetic spectrum. People imagine perfect absorbers and emitters as purely theoretical, while in reality, many materials approximate this behavior closely enough to reveal deep truths. The connection between temperature and color is misunderstood, reduced to simple heuristics, rather than appreciated as a precise and elegant law of nature. Misconceptions obscure the wonder inherent in these patterns, the awe that arises when one sees the unity between mathematics and the natural world. In contemplating blackbody radiation, one cannot help but marvel at the subtle poetry of the universe. Ordinary matter becomes extraordinary when examined through the lens of energy and emission. The quantization of light challenges intuition, yet it harmonizes with experimental reality in a way that feels inevitable and profoundly satisfying. Blackbody radiation teaches patience and curiosity, rewarding those who peer into the quiet glow of heated objects with insights that ripple through the foundations of physics. It is a reminder that the universe is stranger and more intricate than it appears, and that even in the humblest glow of a filament, there exists a doorway to the sublime. Quantum randomness. Quantum randomness is the concept that at the most fundamental level of reality, certain events occur without deterministic cause. Unlike classical physics, where knowledge of initial conditions allows precise prediction of outcomes, quantum systems defy such certainty. This inherent unpredictability is not a result of ignorance or measurement error, but a fundamental property of nature itself. In contemplating quantum randomness, one confronts a world where certainty gives way to possibility, where the universe holds secrets that no calculation can fully unveil. The workings of quantum randomness emerge from the principles of quantum mechanics. Particles such as electrons or photons exist in states described by probabilities. When measured, these probabilities collapse into a specific outcome, yet the exact result is not predetermined. The classic example is the behavior of an electron in a double-slit experiment, where the particle does not follow a single path, but exists in a superposition of paths until observed. Measurement forces a resolution of possibilities, yet which possibility manifests is inherently unpredictable. This is not chaos in the classical sense, for it is not a complex determinism, but a true indeterminacy woven into the fabric of reality. Key evidence for quantum randomness is found in experiments that highlight the limits of determinism. The pioneering work of physicists, such as Max Born, suggested that the wave function of a quantum system provides probabilities, not certainties. The Bell test experiments further reinforce this, showing that no hidden variable theory can fully account for the observed correlations of entangled particles. When photons are entangled and separated by vast distances, measurements on one photon instantaneously influence the state of the other, yet the specific outcome remains random. These experiments illuminate a reality where unpredictability is not an artifact, but a fundamental feature of nature itself. The implications of quantum randomness challenge our deepest intuitions. In a universe governed by quantum chance, causality acquires a nuanced meaning. Events do not follow a strict deterministic chain, but emerge from probabilities. This perspective invites philosophical reflection on the nature of reality and free will. If the universe contains true randomness, then perhaps our conception of choice and chance is more profound than mere illusion. The unpredictability at the quantum level introduces a form of subtle freedom into the structure of existence, a whisper that certainty is never absolute, and that the cosmos holds room for surprise. Quantum randomness also permeates practical applications, shaping technologies that touch daily life. Random number generators based on quantum processes produce sequences that are genuinely unpredictable, essential for secure cryptography. Quantum computers exploit superposition and entanglement, leveraging randomness to perform computations that classical machines cannot. In metrology, quantum uncertainty defines the ultimate limits of measurement precision, guiding the development of atomic clocks and sensors of unparalleled accuracy. Even in medicine and material science, quantum effects influence chemical reactions and molecular behavior in ways that hinge on stochastic outcomes. Randomness is not mere abstraction, but a tangible force shaping innovation. Yet despite its centrality, quantum randomness is often misunderstood. Some imagine that it implies chaos or lack of order, when in truth it is governed by precise probabilistic laws. Others assume that random behavior negates causality entirely, ignoring the structured statistical patterns that emerge over many observations. There is also a temptation to anthropomorphize randomness, attributing it to intention or will, whereas it arises from the fundamental indeterminacy of the quantum world. Recognizing these misconceptions allows a clearer appreciation of randomness as a disciplined unpredictability, a subtle interplay between uncertainty and law. Ultimately, contemplating quantum randomness evokes awe and introspection. It reminds us that the universe is not a clockwork of perfect predictability, but a tapestry in which chance and necessity coexist. The unpredictability of quantum events challenges human ambition to know all, yet it also enriches our experience of wonder. The smallest scales of existence reveal a world in which mystery is built into the very atoms of reality, where every measurement is a dialogue with the unknown. In embracing this randomness, we confront the profound beauty of a universe that is both knowable and forever elusive, inviting thought, humility, and a deep, contemplative reverence for the nature of all that is. Decoherence. Decoherence is the subtle erosion of quantum coherence, the delicate condition that allows particles to exist in multiple states simultaneously. It is the quiet mechanism by which the bizarre superpositions of quantum theory collapse into the classical world we experience. In essence, decoherence is the process that separates the abstract possibilities of quantum states from the concrete outcomes we observe, bridging the chasm between the microscopic and the macroscopic. It is not a collapse caused by an observer, but rather an inevitable interaction with the surrounding environment, a whispering of order into chaos that shapes reality. The process of decoherence occurs through the incessant entanglement of a quantum system with its environment. Every photon, atom, or stray particle that touches the system carries away fragments of information, imprinting the system's quantum state onto the universe. The pristine superposition of states becomes entangled with the myriad possibilities of the surrounding world, causing interference patterns to vanish. It is as though the universe itself acts as a vast witness, recording the state of the system and enforcing classicality without any conscious intervention. The mathematics of density matrices captures this transition, revealing how off-diagonal elements representing superpositions decay exponentially over time, leaving behind only classical probabilities. Experiments over the past few decades have illuminated decoherence in astonishing detail. The classic double-slit experiment demonstrates interference fringes that disappear when the environment interacts with the particles, revealing the fragile nature of quantum coherence. Advanced experiments with superconducting circuits, trapped ions, and photons in optical cavities have meticulously measured the rate of decoherence, confirming theoretical predictions with precision. One striking demonstration involves cooling microscopic objects to near absolute zero and isolating them from all environmental noise. Even under such extreme conditions, decoherence slowly creeps in, a reminder that absolute isolation from the universe is a practical impossibility. The implications of decoherence challenge our deepest intuitions about reality. It renders the notion of a persistent, isolated quantum state illusory, showing that superpositions are inherently transient outside of carefully controlled environments. The universe, in effect, is constantly observing itself, dissolving quantum ambiguity into classical definiteness. This realization is unsettling for anyone drawn to the counterintuitive freedom of quantum mechanics, for it suggests that the strange potentialities we imagine are never truly free to unfold in isolation. Decoherence explains why Schrödinger's cat is never simultaneously alive and dead in our perception, and why the world of macroscopic objects stubbornly obeys classical laws despite the underlying quantum substrate. Despite its abstract nature, decoherence has practical applications that are quietly transformative. Quantum computing relies on the delicate balance of coherence. Understanding decoherence allows engineers to design error correction schemes and shielding strategies that prolong the lifespan of qubits. In quantum cryptography, decoherence informs protocols that detect eavesdropping, exploiting the environment's inevitable imprint on quantum states. Even in emerging fields like quantum biology, decoherence offers a framework to study how fragile quantum effects might play a role in processes such as photosynthesis or avian navigation, hinting at a subtle intertwining of quantum phenomena with the fabric of life. Many misconceptions surround decoherence. It is often mistakenly described as a form of measurement, yet it operates independently of observers. It does not collapse wave functions by choice, but passively enforces classicality through entanglement. Some assume decoherence explains all mysteries of quantum mechanics, but it cannot account for the randomness of individual outcomes, only the suppression of interference between alternatives. Clarifying these points helps distinguish decoherence as a principle of environmental interaction rather than a philosophical or metaphysical statement about consciousness. In closing, decoherence is both a guardian and a liberator, a mechanism that binds quantum potentiality to the observable universe while revealing the fleeting nature of quantum states. It forces a contemplative reflection on the fragility of possibility, the inevitability of interaction, and the quiet artistry with which the universe converts ambiguity into experience. By studying decoherence, one gains not only a tool for technological innovation, but also a window into the subtle interplay between the potential and the actual, between the invisible laws of quantum mechanics and the tangible world that surrounds us. It is a reminder that reality is less about permanence and more about the ceaseless conversation between matter, energy, and the vast environment that enfolds all existence. Schrödinger's cat. Schrödinger's cat is a thought experiment that illustrates the strange and counterintuitive nature of quantum mechanics. It begins with a hypothetical scenario in which a cat is placed inside a sealed box, along with a device containing a radioactive atom, a Geiger counter, and a vial of poison. The atom has an equal probability of decaying or not decaying within a given time frame. If the atom decays, the Geiger counter triggers the release of poison, killing the cat. If the atom does not decay, the cat remains alive. This setup presents a paradox in which, according to quantum theory, the cat is simultaneously alive and dead until an observation is made. The experiment is not about harming animals, but about highlighting the strangeness of quantum superposition and the role of measurement in determining reality. The principle at play is the superposition of states. At the quantum level, particles do not have definite properties until they are measured. The atom inside the box exists in a superposition of decayed and undecayed states, and consequently, the cat is also in a superposition of alive and dead. The act of observation collapses this superposition into a definite outcome. This thought experiment challenges classical intuition by suggesting that the state of a system can depend on whether it is observed. It forces us to confront the idea that reality may not be fixed, and that the act of measurement plays a fundamental role in shaping what we perceive as real. Erwin Schrödinger, the physicist behind the experiment, formulated it in 1935 to critique the Copenhagen interpretation of quantum mechanics. While there is no physical experiment involving an actual cat, related experiments have been conducted with particles, photons, and atoms. For example, physicists have managed to place particles in superposition and observe the collapse of their states upon measurement. The phenomenon of quantum superposition has been demonstrated in numerous laboratory settings, validating the underlying principles that Schrödinger sought to highlight. These experiments show that the paradox is not merely philosophical, but grounded in observable phenomena at the microscopic scale. The implications of Schrödinger's cat extend far beyond the confines of the thought experiment. It forces a reconsideration of reality and the role of consciousness in measurement. If the cat's fate is undetermined until observed, then the notion of objective reality becomes less absolute. This challenges the classical view of the universe as a deterministic machine. Philosophically, it raises questions about the nature of existence the relationship between observer and observed, and the limits of human knowledge. The thought experiment embodies the tension between the predictable world of everyday experience and the unpredictable, probabilistic realm of quantum mechanics, revealing the profound strangeness at the heart of the physical universe. Despite its philosophical weight, the principles illustrated by Schrödinger's cat have practical consequences. Quantum superposition and entanglement form the foundation of emerging technologies, such as quantum computing and quantum cryptography. Quantum computers exploit superposition to perform multiple calculations simultaneously, potentially revolutionizing information processing. Quantum cryptography uses the principles of measurement and uncertainty to create communication systems that are theoretically unhackable. The thought experiment thus serves as both a conceptual lens and a guiding principle for real-world applications that are beginning to reshape technology and our understanding of information itself. Many misconceptions surround Schrödinger's cat. One is the belief that the experiment involves a real cat in a scientific test. Another is the idea that the cat is literally alive and dead in a macroscopic sense. In reality, the experiment is entirely hypothetical and designed to illustrate quantum phenomena in a macroscopic analogy. It also does not imply that consciousness is required to collapse a quantum state. Rather, any interaction with the environment that extracts information about the system can lead to what is known as decoherence, which resolves the superposition in a way consistent with observed outcomes. Understanding these subtleties is crucial to appreciating the depth of the paradox without oversimplifying its meaning. Schrödinger's cat remains one of the most evocative and enduring images in science. It embodies the mystery, elegance, and challenge of quantum mechanics, forcing us to question what we mean by reality, observation, and existence. In contemplating a cat that is both alive and dead, we are invited to confront the limitations of human intuition and the radical nature of the universe. The thought experiment is at once a critique, a guide, and an inspiration, revealing a world where certainty is fleeting and the act of looking can shape the very fabric of reality. In this way, Schrödinger's cat continues to provoke wonder, philosophical reflection, and scientific exploration, a bridge between the invisible quantum realm and the tangible world we inhabit. Quantum gravity problem. The quest to understand quantum gravity emerges from a profound tension in modern physics. On one hand, quantum mechanics describes the universe at the smallest scales with extraordinary precision, revealing a reality woven from probabilities and uncertainties. On the other, general relativity governs the cosmic stage, explaining gravity as the curvature of space and time itself. The problem arises because these two frameworks, each confirmed by decades of experiment, are fundamentally incompatible when confronted with extreme conditions, such as the centers of black holes or the universe at the instant of the Big Bang. At its core, the quantum gravity problem is the search for a coherent description of gravity within the language of quantum theory, a union that promises to redefine our understanding of the cosmos. The mechanics of quantum gravity remain largely hypothetical, yet various theoretical approaches attempt to bridge the divide. String theory proposes that the elementary constituents of reality are not point-like particles, but tiny vibrating strings whose interactions give rise to both matter and gravitational effects. Loop quantum gravity takes a different route, suggesting that space itself is granular, composed of discrete loops that quantize geometry at the Planck scale. Both approaches imply that spacetime is not a smooth continuum, but exhibits a microscopic structure beyond the reach of ordinary observation. In attempting this synthesis, physicists often encounter profound mathematical challenges, reflecting the conceptual strain of reconciling a probabilistic world with a geometrical one. Evidence for quantum gravity is notoriously elusive, primarily because the energies at which quantum gravitational effects become significant are far beyond current experimental reach. Nonetheless, certain phenomena provide indirect clues. Observations of black hole thermodynamics suggest that black holes radiate energy, a phenomenon predicted by Stephen Hawking, hinting at a deep interplay between quantum mechanics and gravity. Additionally, the cosmic microwave background, a relic of the early universe, might contain subtle imprints of quantum gravitational processes. Even tabletop experiments probing minute deviations in gravitational behavior or the nature of quantum superpositions of mass are being explored, but a definitive measurement remains a distant goal, underscoring the subtlety and scale of the challenge. The implications of understanding quantum gravity are found and often counterintuitive. Time and space themselves may emerge from underlying quantum processes rather than existing as fundamental entities. The classical notion of a smooth spacetime continuum could dissolve under extreme scrutiny, replaced by a discrete network of relations. This raises questions not only about the fabric of the cosmos, but also about causality and the very notion of reality at the smallest scales. In black holes, quantum gravity could resolve the paradoxes of information loss, while at the birth of the universe, it could explain the initial singularity without infinities, offering a vision of a cosmos that is both finite and unbounded in its origin. Despite its abstraction, the search for quantum gravity carries potential real-world significance. Technologies such as quantum computing, which rely on coherent manipulation of quantum states, may benefit from insights into the ultimate limits imposed by gravity. Moreover, understanding the interaction between quantum systems and spacetime could inform high-precision measurements, navigation, and even new forms of energy manipulation. While immediate applications remain speculative, the pursuit of fundamental knowledge often lays the groundwork for revolutions that could reshape technology in unforeseen ways, echoing the historical impact of quantum mechanics and relativity themselves. Common misconceptions abound. Some believe quantum gravity is merely theoretical indulgence with no experimental consequence, overlooking the indirect evidence and the guidance it provides for unifying physics. Others imagine it as a mystical or incomprehensible domain, when in fact it is grounded in rigorous mathematics and empirical constraints. The notion that gravity must simply be quantized in the same way as other forces is also simplistic. The challenge is subtler, involving the quantization of spacetime itself and the reconciliation of fundamentally different conceptual frameworks. Ultimately, the quantum gravity problem stands as a testament to the limits of human understanding and the audacity of the scientific imagination. It invites reflection on the nature of reality, the interplay between the infinitely large and the infinitesimally small, and the possibility that our classical intuition is only an approximation to a deeper, more intricate truth. To confront it is to embrace uncertainty, to grapple with paradox, and to glimpse the extraordinary unity that may lie at the heart of the cosmos, awaiting the insight that will render the universe coherent in ways we can scarcely yet imagine. Standard model. The Standard Model is the framework through which we comprehend the universe at its most fundamental level. It is an intricate tapestry of particles and forces, a map of the subatomic world that defines the behavior of matter and energy. At its heart lies a profound simplicity, cloaked in staggering complexity, a structure that explains how quarks combine to form protons and neutrons, how electrons orbit nuclei, and how photons mediate the force of light. It is both a triumph of human intellect and a reminder of how much remains mysterious in the cosmos. The Standard Model does not merely catalogue particles. It reveals the deep symmetries and patterns that govern existence itself, offering a lens through which the invisible becomes perceptible. The mechanics of the Standard Model, rooted in the interplay of fundamental forces and particles. There are 6 types of quarks and 6 types of leptons, each with distinct properties, interacting through gauge bosons which carry forces. The electromagnetic, weak, and strong forces are described mathematically with elegant precision, governed by symmetry principles that suggest an underlying order to the universe. Particles acquire mass through interactions with the Higgs field, an omnipresent entity that imbues the void with substance. In this structure, every particle and every force is bound together by mathematical relationships that predict behavior with uncanny accuracy. The harmony is delicate, and even a minor deviation could have made the universe unrecognizable, devoid of the matter structures that sustain life. Evidence for the Standard Model emerges from decades of careful experimentation and observation. Particle accelerators, such as the Large Hadron Collider, smash particles together at near light speeds, revealing ephemeral entities that exist for fractions of a second yet validate theoretical predictions. Detectors observe decay patterns, scattering processes, and energy distributions that confirm the existence of quarks, leptons, gluons, W and Z bosons, and the elusive Higgs particle. Experiments like these are profound dialogues between theory and reality, where abstract equations are confronted with the physical world, each collision illuminating the fabric of matter. Every successful prediction reinforces the model, yet every unexplained anomaly beckons the mind toward deeper understanding. The Standard Model is peculiar in ways that provoke philosophical reflection. It is remarkably accurate, yet incomplete. It does not account for gravity, the force that shapes galaxies, nor does it fully explain dark matter, or the asymmetry between matter and antimatter. It posits particles without offering insight into why their specific properties exist. There is an almost mystical quality in this explanatory power that stops short of ultimate understanding. The model is precise, but silent on questions of origin and purpose, a testament to the limits of human reason and a prompt to wonder at the vastness beyond our current grasp. The universe as revealed by the Standard Model is both intelligible and enigmatic, offering answers that deepen the mystery. Despite its theoretical abstraction, the Standard Model has profound implications in the real world. It underlies technologies that shape daily life, from the semiconductors in computers to medical imaging devices that peer into the human body. It guides the development of particle accelerators and radiation therapies, influencing both research and practical applications. The principles governing electromagnetic interactions allow the creation of lasers, magnetic resonance imaging, and even the materials in everyday electronics. In understanding the subatomic, we gain leverage over the macroscopic, applying insights into engineering, medicine, and energy production in ways unimaginable without the model as a foundation. Common misconceptions about the Standard Model arise from its abstract nature. Some assume it explains all of reality, or that it unifies all forces, yet it deliberately omits gravity. Others believe particles exist in isolation, ignoring the interdependent relationships that define their behavior. It is not a theory of everything, but a theory of most things within a specific domain. Misunderstanding also comes from conflating the model with philosophy, attributing metaphysical significance beyond its empirical and mathematical scope. Recognizing these limits is as important as celebrating its triumphs, for clarity in comprehension reserves the model's integrity and its place in the broader quest for knowledge. In reflecting upon the Standard Model, one cannot help but sense awe. It is a construct of human reason that captures the subtle dance of the universe, revealing order where chaos might have reigned. It invites contemplation of the elegance underlying reality and the persistent mysteries that elude our grasp. Though incomplete, it is a cornerstone of modern physics, a testament to inquiry and imagination. The Standard Model reminds us that understanding is provisional, that each answer unfolds new questions, and that the universe is simultaneously knowable and profoundly strange, offering endless horizons for curiosity and discovery. Quantum fields. Quantum fields are the underlying fabric of reality from which all particles emerge. They are not particles themselves, but pervasive entities that exist throughout space and time. Every particle that appears in the universe is a localized excitation of its corresponding quantum field. In this sense, The universe is not made of solid matter or empty void, but of fields vibrating with potential, each ripple manifesting as the observable particles we interact with daily. The concept challenges the traditional notion of objects as isolated, permanent entities, inviting a reconsideration of what it means to exist. The operation of quantum fields is both subtle and profound. At the most fundamental level, these fields follow the rules of quantum mechanics, exhibiting probabilistic behavior and uncertainty. Particles emerge when a field vibrates at certain energy levels, and these vibrations are influenced by interactions with other fields. The quantum fields are also relativistic, ensuring that their behavior remains consistent with the structure of spacetime. Unlike classical waves, these fields are quantized, meaning energy can only be transferred in discrete packets. Fluctuations in these fields are never zero, even in a perfect vacuum, producing ephemeral particles that flicker into and out of existence, suggesting that the vacuum itself is a seething, restless medium. Evidence for quantum fields arises from experiments that probe the very boundaries of matter and energy. The detection of the Higgs boson confirmed the existence of the Higgs field, which imparts mass to particles, making the physical world possible. Electron-positron pair creation, observed in high-energy particle collisions, illustrates how energy in a field can materialize as particles. The Casimir effect demonstrates that empty space has measurable energy due to quantum fluctuations, affecting the behavior of macroscopic objects. Precision measurements of the magnetic moment of the electron match predictions, derived from quantum electrodynamics, to astonishing accuracy, reinforcing the reality of quantum fields even when they cannot be directly seen. The implications of quantum fields stretch beyond mere physical predictions. They suggest that the world is not composed of discrete objects, but a dynamic interplay of continuous processes. Matter and energy are temporary manifestations of underlying potentials. Even the concept of locality becomes ambiguous, as quantum fields can entangle distant regions in ways that defy classical intuition. These fields challenge the human desire for deterministic narratives, confronting us with a universe that is fundamentally probabilistic, fluid, and interconnected. In contemplating quantum fields, one glimpses the delicate balance between the seen and unseen, the measurable and the ephemeral. In practical terms, quantum fields underpin technologies that have transformed modern life. Semiconductors, the backbone of electronics, rely on principles of quantum field interactions. Lasers exploit the coherent excitation of electromagnetic fields. Magnetic resonance imaging manipulates quantum spin fields to visualize the interior of the human body. Even emerging areas like quantum computing and quantum communication exploit the peculiar properties of quantum fields to achieve feats impossible within classical frameworks. Each application is a testament to the profound ways in which these invisible fields shape tangible reality. Misconceptions about quantum fields abound, often arising from attempts to translate them into familiar terms. It is sometimes imagined that quantum fields are like waves on a pond or invisible substances filling space. Such analogies fail to capture the true abstract nature of fields, which are not located in space, but are the very definition of space in their interactions. Particles are not tiny balls riding on fields, but excitations of the fields themselves. Additionally, quantum fields are often thought to act only at microscopic scales, whereas their influence permeates every aspect of the universe, from the tiniest electron to the largest galaxy. Quantum fields invite both scientific inquiry and philosophical reflection. They remind us that reality is richer and stranger than our everyday perception allows. Observing their effects challenges intuition, revealing a world where existence is continuous and discrete, deterministic and probabilistic, visible and invisible. The study of quantum fields is not merely a technical pursuit, but an invitation to reimagine the cosmos and our place within it. Their presence is a quiet, omnipresent testimony to the profound intricacy and subtle beauty of the universe. In contemplating them, one is left with a sense of wonder, humility, and the recognition that the deepest truths often lie beneath the surface of what can be seen or touched. Quantum tunneling in stars. In the heart of a star, an invisible drama unfolds. Particles behave not as solid, predictable objects, but as entities governed by probabilities and strange possibilities. Quantum tunneling is the key to this mystery. It allows particles to cross barriers that, according to classical physics, they should never surmount. Deep within stellar cores, where temperatures reach millions of degrees and pressures crush with unimaginable force, this phenomenon enables the nuclear reactions that power the cosmos. Without quantum tunneling, the fusion of hydrogen into helium would be impossibly slow, and the stars we see scattered across the night sky would never shine with their serene brilliance. At its essence, quantum tunneling emerges from the wave nature of particles. Every particle possesses a probability wave that describes where it might be. When particles collide in stellar cores, they face an energy barrier, a wall of repulsive forces that seems insurmountable. Classical physics predicts that only particles with energy exceeding the barrier could proceed. Yet the quantum world defies such certainty. There exists a non-zero probability that a particle can be found on the other side, appearing as if it has passed through the barrier itself. In stars, this allows protons to overcome their mutual electrostatic repulsion and fuse, releasing vast amounts of energy. The process is governed by equations that blend the abstract mathematics of wave functions with the tangible reality of stellar luminosity, a bridge between the unseen quantum realm and the observable universe. Experimental and observational evidence underpins our understanding of tunneling. The study of nuclear fusion rates in laboratories simulates, on a tiny scale, the conditions within stellar cores. Experiments with particle accelerators reveal reaction rates consistent with tunneling predictions. Moreover, neutrino measurements from the Sun provide indirect evidence, confirming that fusion occurs at rates that would be impossible without tunneling. The patterns of light and energy emitted by stars across the spectrum align precisely with theoretical models that include the influence of quantum tunneling, reinforcing the notion that this ethereal process is not merely theoretical but a concrete actor in the universe's theater. The implications of quantum tunneling are profound and somewhat unsettling. It challenges intuitive notions of causality and possibility, revealing that the universe allows events to occur that classical logic would forbid. In the context of stars, it ensures that fusion begins at temperatures far lower than would otherwise be required, making stellar lifetimes longer and more stable. It reminds us that the cosmos is not a mechanical clockwork, but a delicate interplay of chance and necessity, a place where uncertainty underpins creation itself. The very warmth of the sun, the existence of elements, and ultimately the conditions for life hinge upon this improbable quantum ballet. Beyond the stellar context, the understanding of tunneling has practical repercussions. It is the principle behind modern technologies such as tunnel diodes, scanning tunneling microscopes, and even certain semiconductor devices. In each case, particles traverse barriers that would be insurmountable by classical energy considerations alone. This insight, first glimpsed in the cores of stars, has become a cornerstone of quantum electronics, enabling innovations that shape contemporary life. The stars, in this sense, serve as natural laboratories, their interiors offering lessons that guide human ingenuity in crafting devices that exploit the same enigmatic rules. Common misconceptions abound, perhaps because the process seems so counterintuitive. Tunneling does not mean that particles vanish and reappear at random. It is not magic, but a calculable probability dictated by the wave function and the barrier's characteristics. It does not violate energy conservation, but rather exploits the probabilistic nature of quantum mechanics to allow events that, while unlikely, are entirely consistent with physical law. Recognizing these subtleties is essential to grasp the delicate balance between certainty and chance that governs the microscopic world. Ultimately, quantum tunneling in stars invites reflection on the hidden depths of reality. It challenges our sense of inevitability, revealing that the cosmos is sculpted by processes both subtle and profound. The gentle light of a distant star carries within it the testimony of particles overcoming impossible odds, of the improbable shaping the inevitable. By contemplating this, we touch a deeper understanding of existence itself, perceiving a universe that is both fragile and resilient, predictable and astonishingly creative. In every beam of starlight lies the quiet marvel of quantum mechanics, a reminder that the universe is at once comprehensible and endlessly mysterious, and that the smallest acts at the subatomic level can illuminate the grandest structures we behold. Casimir effect. The Casimir effect represents one of the most curious phenomena in quantum physics, a subtle force emerging from the vacuum itself. It is the quiet murmur of the universe revealing that emptiness is not truly empty. When two uncharged, parallel metal plates are placed exceedingly close together in a vacuum, they experience an attraction that cannot be explained by classical physics alone. This effect is a tangible consequence of the quantum fluctuations that constantly ripple through the void. It challenges the very notion of nothingness, suggesting that even in complete absence, the universe hums with potential and imperceptible energy. At its core, the Casimir effect arises from the peculiar nature of quantum fields. In quantum theory, empty space is never void, but filled with fluctuating electromagnetic waves of all possible wavelengths. When two plates are brought near each other, they impose restrictions on the wavelengths that can exist between them, allowing only certain modes of vibration. Outside the plates, however, all wavelengths are permitted. The imbalance in pressure between the constrained interior and the unconstrained exterior generates a net force, drawing the plates together. This subtle, almost ghostly force illustrates how the structure of the vacuum itself dictates physical interactions, revealing a universe that is more active and intricate than our senses suggest. Experimental evidence for the Casimir effect began to accumulate in the latter half of the 20th century. The earliest precise measurement was conducted by Marcus Barnett, who detected the predicted attraction between parallel metal plates in a vacuum. Later experiments refined the understanding of the effect, confirming that it is sensitive to the shape, separation, and material properties of the surfaces involved. In 1997, Steve Lamora performed one of the most celebrated experiments using a torsion pendulum, measuring the force with remarkable precision. These empirical investigations transformed what was once a theoretical curiosity into a verified physical phenomenon, affirming that the fluctuations of the vacuum exert measurable influence on the material world. The Casimir effect is profoundly strange because it arises from nothing tangible, from the empty space we often disregard as inert. It forces a confrontation with the paradoxical notion that absence can exert presence, that emptiness can carry force. Philosophically, it nudges us to reconsider our assumptions about reality. The universe does not require matter to enact change. In this way, the Casimir effect exemplifies a subtle harmony between the seen and unseen, the tangible and intangible, revealing the depths of order hidden within apparent chaos. It reminds us that the universe operates on principles that are at once precise and mysterious, defying the simplicity our intuition craves. Despite its ethereal origins, the Casimir effect has practical implications. In the field of nanotechnology, as devices shrink to microscopic scales, Casimir forces become increasingly significant, affecting the behavior of microelectromechanic systems. These forces must be accounted for in the design of nanoscale machinery, where they can lead to sticking or unwanted attraction between components. Some researchers have even speculated about harnessing Casimir forces for novel forms of propulsion or energy manipulation. While these applications remain largely speculative, They hint at a future where the vacuum itself could be an active component of technological innovation. Common misconceptions about the Casimir effect often arise from its mysterious nature. Some imagine it as a form of perpetual motion or as a source of limitless energy. In reality, it is a finite, well-understood quantum phenomenon governed by the rules of physics. Others mistakenly attribute the force to classical electromagnetism or to van der Waals interactions, but the Casimir effect is distinct, arising specifically from the modification of vacuum fluctuations. Understanding its precise origin requires careful attention to quantum theory, reminding us that intuition shaped by everyday experience is often insufficient when confronting the subatomic realm. Ultimately, the Casimir effect offers both a window into the unseen dynamics of the universe and a challenge to our perception of reality. It embodies the subtle interplay between absence and presence, revealing that the vacuum is far from inert. It invites reflection on the hidden structures and forces that underpin existence, suggesting that even in emptiness, there is a profound richness to be discovered. By studying this phenomenon, we not only gain practical insights into quantum engineering, but also cultivate a deeper philosophical awareness of the universe as an intricate, vibrating web of possibilities. In contemplating the Casimir effect, one is reminded that reality is layered, mysterious, and alive with unseen influence. High-precision predictions. High-precision predictions are the remarkable capacity to anticipate events or outcomes with extraordinary accuracy. At first glance, the concept seems almost mystical, a domain reserved for prophecy or intuition. Yet beneath this veneer lies a foundation rooted in observation, data, and patterns that often elude immediate human perception. These predictions operate in a liminal space where mathematics, cognition, and environmental signals converge, revealing tendencies that would otherwise remain invisible. The fascination with high-precision predictions stems from the tension between the apparent certainty they offer and the inherent uncertainty of the world. To ponder them is to confront the delicate balance between what can be known and what forever escapes understanding. The mechanisms that enable such predictions are subtle and intricate. They emerge from the systematic collection of information and the application of rigorous analytical frameworks capable of discerning correlations and causations within complex systems. Computational models simulate countless scenarios, iteratively refining outputs until they converge on results with minimal deviation. In parallel, human intuition, honed by experience and context, can detect patterns that elude algorithmic reasoning. Feedback loops allow constant recalibration, and the synthesis of diverse data sources creates a lattice of predictive insight. The precision achieved is often not the product of a single element, but the harmonious orchestration of multiple factors, each contributing its whisper to a larger chorus of foresight. Experimental evidence underscores the surprising effectiveness of high-precision prediction. In fields ranging from meteorology to epidemiology, models have been able to forecast storms or disease outbreaks with levels of accuracy previously deemed impossible. Controlled experiments in cognitive science reveal that experts can anticipate human behavior in structured settings with striking reliability. Even in financial markets, sophisticated algorithms that assimilate vast quantities of historical and real-time data can generate predictions that outperform conventional intuition. These experiments illuminate the principle that while the future remains fluid, its contours can sometimes be traced with remarkable clarity. The implications of such precision are as profound as they are unsettling. There is a paradox in knowing what will likely unfold while still inhabiting a world defined by chance. It challenges the notion of free will, for to anticipate with near certainty the choices of individuals or systems is to confront the possibility that autonomy may exist within invisible boundaries. The strange allure of high-precision prediction lies in its ability to make the improbable seem inevitable, to transform uncertainty into an ordered map. It provokes philosophical reflection on the nature of knowledge, the limits of perception, and the interplay between determinism and randomness. Practical applications demonstrate the transformative potential of this capability. Urban planners can design cities resilient to floods or traffic congestion, informed by predictive simulations. Public health officials deploy models to preemptively mitigate the spread of disease. Businesses optimize supply chains by anticipating consumer behavior and market fluctuations. Even personal technologies, from predictive text to recommendation systems, subtly guide decisions, reflecting the pervasive influence of anticipatory knowledge. In each case, the predictive framework serves as a bridge between observation and action, converting insight into a tool for shaping outcomes. Yet misconceptions abound. High precision does not equate to absolute certainty, and it cannot annul the inherent variability of complex systems. Predictions are probabilistic, their accuracy contingent upon the quality of input data and the fidelity of the models employed. Another common error is to conflate correlation with causation, assuming that repeated patterns guarantee future replication. There is also a tendency to overlook the subtle influence of human behavior, randomness, and unforeseen variables that can disrupt even the most robust forecasts. Understanding these limitations is essential to appreciate both the power and the fragility of predictive insight. Ultimately, high-precision predictions inspire not simply for their technical prowess, but for the philosophical questions they evoke. They compel us to examine the boundary between knowledge and uncertainty, between control and surrender. In contemplating their capacities, one is reminded of the elegance inherent in the natural and human systems they seek to interpret. They are a testament to the interplay between observation, intellect, and imagination, revealing a universe where patterns exist yet are never fully captured, and where the pursuit of understanding is as profound as the knowledge itself. Weirdness of quantum mechanics. Quantum mechanics is the branch of physics that explores the behavior of matter and energy at the smallest scales. Unlike the predictable movements of planets or the steady flow of rivers, the quantum world is a realm of probabilities, uncertainties, and phenomena that defy classical intuition. It confronts us with a reality where particles can exist in multiple states at once, where observing something changes its behavior, and where connections between entities seem to transcend space and time. To approach quantum mechanics is to step into a landscape that challenges the very foundations of what we consider real and comprehensible. At its core, quantum mechanics relies on mathematical formulations that describe the evolution of systems in terms of wave functions. These wave functions encapsulate all possible outcomes, and until a measurement occurs, the system exists in a superposition of these outcomes. This framework is governed by principles such as the uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. The theory is counterintuitive because it denies the deterministic certainty we expect from everyday experience, replacing it with a probabilistic nature that only crystallizes into a single reality when observed. The experimental foundations of quantum mechanics are as striking as the theory itself. The double-slit experiment reveals that particles like electrons can interfere with themselves as if they were waves, yet manifest as particles when measured. Quantum entanglement demonstrates that particles separated by vast distances can instantaneously influence each other, a phenomenon Einstein famously called spooky action at a distance. Experiments with quantum tunneling show that particles can pass through barriers that classical physics deems impenetrable. These observations are not just theoretical curiosities. They are verified with extraordinary precision, repeatedly confirming that the quantum description of reality, however strange, corresponds with the behavior of the physical world. The implications of these discoveries are profound and intellectually unsettling. quantum mechanics undermines the notion of objective reality as a fixed and independent entity. It forces us to accept that at a fundamental level, reality is not composed of isolated objects with determined properties, but of possibilities, potentials, and relationships. Cause and effect take on a nuanced character where outcomes are contingent upon context and measurement. The world becomes a participatory system, where the act of observation is inseparable from the unfolding of events. In this light, the weirdness of quantum mechanics is not merely a collection of puzzling phenomena, but a window into a universe that is more fluid, interconnected, and enigmatic than classical intuition allows. Despite its abstract nature, quantum mechanics has concrete applications that shape modern technology. Semiconductors and transistors, the building blocks of computers and smartphones, operate on quantum principles. Lasers, which underpin everything from medical devices to telecommunications, rely on the controlled emission of photons, as described by quantum theory. Quantum cryptography offers the promise of virtually unbreakable communication, exploiting the principles of superposition and entanglement to detect eavesdropping. Emerging technologies in quantum computing aim to harness superposition and entanglement to perform calculations beyond the reach of classical machines, potentially revolutionizing fields from material science to artificial intelligence. Public understanding of quantum mechanics is often clouded by misconceptions. People may imagine particles as tiny billiard balls moving unpredictably, rather than entities with probabilistic properties that can exist in multiple states simultaneously. Entanglement is sometimes mistaken for instantaneous communication in a classical sense, ignoring the subtleties of information transfer and causality in the quantum framework. These misunderstandings arise because the quantum world operates under rules so different from everyday experience that intuitive analogies can mislead more than they illuminate. Appreciating quantum mechanics requires both humility and a willingness to suspend preconceptions about how the universe should behave. In contemplating quantum mechanics, one cannot help but feel a sense of awe at the elegance and strangeness of nature. It challenges the boundaries of human understanding, revealing that the universe is not a rigid, predictable machine, but a tapestry of interwoven possibilities. The weirdness of quantum phenomena invites reflection on the limits of perception, the role of consciousness in the physical world, and the profound mysteries that remain at the heart of reality. To engage with quantum mechanics is to recognize that the universe is both stranger and more beautiful than our classical imaginations could ever have conceived.